All right. What is a rooted node tree? We are going to build one, but I have to make sure that we are broadcasting. Let me just check real quick here. Yep. I'll go ahead and put a mark in it. Ready, start. Okay. What is a rooted node tree? Some of this stuff I've covered before, so I'm going to cover it really fast, just as a review. I'm trying to shorten the video down so that you're not watching a lot of my flubbing up and going slowly, but some of it's good because I want you to see that, you make mistakes in the process, kind of like Mr. Rogers trying to build that tent that one day. So what is a node tree? Well, a rooted node tree is something you can study in computer science. You'll hear it. It's in the big thick books. We talked about it yesterday. We tried to find a copy of it, but I'm going to go ahead and summarize it even more quickly. So a rooted node tree, use them all the time. Use them in the web. The document object model in the web is a rooted node tree. So like if you have a web browser up, you can just go in and open it up and look. I'm trying to find a good web browser content here to show you. It's this data structure that exists all over, right? So if I have a web page, so let's go to my old rwx.gg site, which hasn't been updated in rwx, not xx. And this is an old site, but you do inspect element, and you can see over here, you see the inspector, you see all of these little things here. And if you go to the console, you can do console.log document, which is the root node for the document object model. And you click here and you can see you got all of these things. You got all these attributes. It's really messy in here. We don't want to make one like this. We're going to make one much cleaner. It's really, really, really messy, right? So this is all the events that go with it and everything. But most importantly here is child. Where is it? Node first child. That's really important. First element child. I mean, this is like a tree within a tree. It's crazy. But where is it? Node. We're looking for node children. And you can, let's just do the same sort of thing with first children. So you can expand on this and see the child nodes, and then this child node has child nodes, et cetera, et cetera. So the idea is that you have a tree. Another place that you see these used all the time is when doing any kind of parsing. So it's something called an abstract syntax tree, which is the reason I'm here doing this. So the pagan language is a notation that I made to expand on Brian Ford's peg grammar. And if you go to pagan.dev, you can open up pagan.dev and you'll see an example of an AST. So this here is a grammar for representing any kind of grammar, language, whatever. We won't talk about that. That's talk about in a different video. But if you want to, then you can go see the abstract syntax tree, which also has its own grammar specification. But here's an example of an AST. This is actually the example of the AST that I want to make today. And the tree, right? So we have a top level grammar tree, and then that each node in the tree has an identifier, right? And it has one or more children, right? And it either has one of two things. And so here's another node right here. So this is what they call a leaf node. That means it's at the very end. So this leaf node, or this final node, whatever you want to call it, this has an actual value instead of children, right? So there's nothing that comes under it. It is like the final thing. And this particular AST is only strings here. And we're going to talk about different ways to do that. But, string trees are the most prominent to use, but we're going to build a system that you could use any way you want to, but we're going to make it so that if you want to do it of trees, of strings, we can do that. We're actually going to talk about how you could use generics, Golang generics to help with this sort of thing. And if there's anybody else out there who's had experience, please chime in. You're welcome to join me on Twitch right now if you're doing this live. So we're going to keep going here. So what else do we have? We have so as you can see, there's like 3 levels of nesting here. So this is a really good example of it. Well, why do you care? Why would you make something like this? You make something like this so that you can create an application like Pandoc, so that the Pandoc is, if you don't know what Pandoc is, it's this famous tool for converting between different document types. So you go between HTML and Markdown, that's the default, right? Or Markdown and HTML. And the way to do that, to be able to support all those different things, is there has to be a common center format that can be gone to, and then from that you can go to something else. Well, that common format is an AST. So if I'm in here and I'm like reading this README, this README is a Markdown file. It's a Markdown file, there's nothing in it, right? But if I were to do pandoc and then just do it on the README file, you see it would use the default, and it would convert it from this Markdown file. So it converts it from this into this. You can actually do it live while you're editing it. You can go bam, bam. Here, let me show you my S keys really quick. It's a whirlwind overview of what we're doing here, but so bang, bang, and then I can do pandoc, and that will replace the file in place, right? But I could also replace it to this intermediate step, which is native, I think it's native. Yeah, there it is. So this is Haskell code. So Pandoc is written in Haskell. Haskell is a really great functional language for producing functional parsers, which I'm going to do in a different video set. But for right now, we're going to go ahead and produce this video. So, and this is kind of verbose. So this is the same idea as what I had before, except for it's really verbose. I mean, it's got, extra spaces and stuff. If you know anything about JSON, you can do the same thing. I can convert this whole thing to JSON. So that we have a JSON file, and as you can see, it's like not very pretty, right? It has an API version. It's got a lot of things in it. I could actually convert that into YAML if I wanted to. I could do, let's do pandoc dash t JSON, pipe that to YQ. Let's see if we would get, yeah. So there, whoops, we're gonna need an eval on that. So I think I need an E on that. Yeah. Nope, that's not going to work. Oh, well, we'll do it later. But you get the point, right? So you've got this common AST that you have to go to in the middle. And that's what I was showing you with the Pagan project I have, because it's trying to be the one like destination format for everything. So it's the only parser, peg parser out there that actually has opinions about what the AST should look like and how it's generated, etc. Right? So those are all valuable things in the world of languages and grammars, which is what I love. I live there. I like this also. But in order to do any of that, you need a node tree. Another example of a node tree would be if you wanted to make a Zettelkasten and registry. So you want to take all of your Zettels and your slips of paper sort of, and you wanted to organize them and give them an outline. Or if you want to do a mind map is at the internet, right? They're all graph types, and a graph type is just a bunch of things that are connected. So if you go back to here, a graph type in this case would be, okay, I got a graph over here. Yeah, we got this. What else we got here? We got another one over here. I got one up here. So this is a graph type. I got a lot of stuff here, right? And it's like the internet. So graph theory, you can go watch Wolfram talk about this. He's made a whole business and life out of it. But this idea of traversing, getting to all the points in a graph, it's very important. It's a central part of machine learning, with you have lots of neural network nodes and things. So understanding the graph idea is super important, but in a practical sense, understanding a rooted node tree is probably the most important. So a rooted node tree is one where, I don't like the block on those arrows, but oh well. I wonder if I can just delete them. Let me try this for a second. So a rooted node tree is one where you have parents and children, so to speak. So, and we kind of talked about it already. How do I fix my arrows? I don't want blocky arrows. I want the non-blocky ones. There, okay. So now we can connect these, right? Yeah, and over here, I should go. No, yeah, I guess this is fine. I don't care. So this is a rooted node tree. That means you got a root, right? So you can put a little text icon on this and call this one root. I mean, I know that's kind of small, so oopsie. I mean, I should probably have a better tool for this, but oh well. I need to zoom it in. We need to zoom that in, make it bigger so you can read it. Can you read it? Let's do 300%. That's kind of big. Oh well. This is Draw.io, by the way. If you want to get it, it's a free tool you can get. Okay, so yeah, we're gonna delete that guy. So you have this text. Let's actually make that text bigger, assuming it would get bigger, but I guess not. So make that font size bigger. Font size needs to be bigger, like 18 or something. All right, so this up here is the root. And then what, right? So you have these children down here, but then the whole point of this thing is to be able to add, you made an interpreter based on a node tree. Yeah, that's generally what you would do. We're doing that same thing. So to do this kind of thing, to make one of these, you have to start out with a root node, and then that root node has children, right? But the whole point of a root node is you want to be able to just delete out a piece of the root node. So this like first one here, and you want it to be okay, right? You want it to survive. And in that sense, you want to be able to just add things so that each individual entity can be by itself. You can actually have, orphaned or unassociated nodes out here that you could create. And then you could actually say, hey, I want to put this node in the tree somehow, right? And then so you want to add that association somehow back to the whole thing. And to do that requires some coding, but you need to think about all the things that you have that are doing this. Okay, so we have it's the two children here, right? And I'm just going to jump right in and tell you the standard way to do this, and then you can think about how you do it. The ultimate goal, though, is we want to be able to take that AST or that node tree, and we want to be able to walk the tree. Now, to be able to walk a tree means that you're going from top to the bottom, and there's all kinds of theory and writing about how to most effectively traverse a tree. I mean, I'm not going to talk about any of that. I'm going to use my particular way, which is very basic and is good enough for my purposes. But there are people who will do extraordinary amounts of theoretical computer science to decide the fastest way to traverse the tree. But thank God that when we have a rooted node tree, it's pretty easy to know how to descend in there and to go to every single thing, right? In sort of a linear way. And so the way that we're doing it is not going to be the fastest, but the idea is you want to be able to do something with all of it, so that you can then, in the case of Pandoc, you want to be able to convert it as you go through the rooted node and everything. You want to be able to create text that is the converted version of the other type that you had before that became an AST, and you want to just go to the next thing. So we need to be able to traverse the tree really quickly, but before we can even do that, we have to create the thing, right? And how you traverse the tree depends on how you associate these different pieces of the tree, right? So I'm going to try to do this with arrows, but so we have this rooted node. All of these are nodes, and then down here we have a child, right? So I'm going to call this. Let's call this. I'm going to give it a property. We're going to say that is the first child. All right, and because I don't know, it's just the first one, right? And then if you want to, I mean, you can think of it this way. You can have this one be the last child. And you don't need a last child, but last child is kind of nice for migrating and for navigating and stuff, and we'll talk about that later. So here we have a root, we have a first child, a last child, and there's all the stuff in between, right? Now, your first inclination, the intuitive thing would be to do this, and I learned this myself. It was really difficult to learn this at first, but the intuitive thing is to do this. You want to say, I'm going to have... right here, I'm going to say, well, what is this, right? Is this second child or third child? Well, the truth of the matter is we don't care about the children in the middle. And there's going to be so many like weird like aphorisms and things that I say that are not real in real life, like killing children and parents and stuff. I don't mean anything that bad about that. So this guy we actually don't care about. Why? And I know this is going to sound really crazy, but if we're thinking about traversing the tree, I'm already thinking in advance. Okay, I'm going to go to the root child. I'm going to say, well, give me my first child. Okay, well, here's my first child. So that means I have to know about the root has to know about his first child. And then it says, all right, so here's my first child. And it's like, okay, I want to do something to all of my children. And it's like, well, I don't know who all my children are. And initially it seems very counterintuitive. You think, oh, I want a list inside of this root node that has all my children in it. But see, that gets us into trouble. As a middle child, I can confirm this. How's it going, Green? Yes, I'm having a great day. So the funny thing about this is that honestly, the first child, and so the first child, by the way, has up here let's put parent. Okay. So this one has a parent. All right. So when this is looking up to here, it looks at that as a parent. The parent only cares about the first and the last child. It does not care about the middle children. And it has to go and say, so what it's going to do actually is it's going to say, hey, first child, hey, eldest child of mine, you know all your siblings, right? So I have something that I want you to do to all your siblings. I want you something to share, because the parent's like, I ain't got no time for that. I'm not going to try to keep track of all my children. I can't possibly do that. So it gives a responsibility of keeping track of all of the other children to the first child. And the only thing the first child's like, I am totally too busy to keep track of all these children. There's like so many stinking children, right? And so let's actually make another one. This represents all middle children. So I'm an oldest, so I'm just going to own that. Anyway, so let's actually join these. Oh boy, wrong thing. Wrong thing indeed. I forgot the join command. I think it's, what is join? Is it union? It's group. Duh. All right, so we're going to group these. I'm going to group these. I'm going to group these together just in case while I'm moving them, I don't get all messed up. All right, so, damn it. So, I'll group these. How about that? We'll group these right there. All right, okay. So there we go. So we have, the plight of all middle children. They seem like they're forgotten, but they kind of have associations with their first child, right? So the algorithm goes like this, and this is, data structures and algorithms kind of thing. This is just one algorithm, but this is the one I'm going to use. So the root parent says, I have something to do. I want you to do something. I want you to pass this message on. I want you to have every single one of my children write out what their type is and what they have in their pockets or something, right? I mean, just pretend for that. So the parent says, okay, you are going to pass, I'm going to delegate this. I'm not going to actually try to do it to everybody here, because if he did, he's like, okay, I'd have to keep track of all the children. That means there would be some spot in here. And that means believe it or not, if a middle child were to die or somebody were to die, then this thing inside of the parent would have to be updated. And that's what we want to avoid. We want the parent's really lazy. It doesn't want to have to put anything. It can maintain some list of all its children and everything. It has so many of them. And sometimes the children are adopted. Sometimes the children come in or given to the parent without the parent even knowing why, right? All of that stuff can happen freely without the parent even knowing, right? So, because it doesn't really need to know, and so what does it do? So the parent goes to the first child and says, hey, who is your first sibling, right? So and if you want to, you could say, who is your next sibling, right? And because it's the first child, I could say, so it has a relationship like this. It bonds it to here. Whoopsie. It's going to get tough, isn't it? Because I did that stupid thing. I joined it. Actually, no, I can do this. Okay. I can do this. I'm capable. Sort of. So come on. I just want that right there. That little dot right there. How do I do this? There we go. Okay. So to this guy over here. Is that going to put it as a part of this other thing? I hope not. Okay, good. All right. So this one over here is the sibling, right? So we'll just say sib, because it's too much to write sibling. It's like too long. So there you got a sibling, and then this guy, also, or girl or a gal or whatever, has another sibling. right? So come on. No, I don't want that. I think it'd be better with my arrows and stuff. I'm not. So here we have, come on, guy. No, I know I can do this. I swear. You know what? I'm just going to do this. Can I just, how do I do an arrow from here? I want an arrow from here. Yes. All right. So I wonder if I could just attach them. They're giving me trouble now. They weren't giving me trouble before. All right, fine. I'm going to do that. Okay. That was easy. I don't know why. Okay. So we have another sibling here, right? So this one's got a sibling here. And we have a sibling there, right? Well, this guy, we have a problem here because what does this guy do? What if the first child dies, right? This is diagram software in a nutshell. It kind of is. I'm sorry, but so what if the first child? I know it's a morbid thought, but what if the first child dies? Who's the parent gonna delegate everything to and try to figure out everything? Well, then this person becomes the first child, right? And I don't want to show that because I have to redraw my thing. So it's actually important that you know who the sibling is over here, right? So in this particular case, there is no sibling over here. There's just a big empty nothing, right? Same with the last child. So we have a big empty nothing. It is a very weird family situation. So we have, so the last child doesn't have any siblings to pick on. and the first child doesn't have any, he's dominant, or she's dominant. She doesn't have anything in the front, right? So we need to figure out a way to name all of this stuff and organize it. And then this is leading somewhere, I promise. So this one really is the sibling to, we'll say, the right. So that's the right sibling, you know, not the correct sibling, the sibling to the right. And yeah. And then this one, so this, to this person, that's the sibling right. So in terms of this one here, though, if we actually, so let's change the arrow here. Let's make the arrow going from here to here. So this one is the sibling to the left. Now I'm using the sort of UML style of naming. I'm putting the name on the thing as this person sees it. So like this node is like, okay, that's my sibling to the left. It does not have a sibling to the right, right? And this one has, so that's the first child, right? And actually, let's take the parent and put it over. Whoa. Let's take the parent and let's ungroup that for a second. Did I ungroup it? No. All right, fine. Just delete you. And I'm going to take this one and turn this one around too. Okay. So let's pretend I'm just trying to show you all the relationships that exist. These relationships exist for every node, by the way. Every node has one. It's just whether or not that it has it or not, if it's nil or not, right? So that's where this is headed. So this one though, let's go back to parent. Where's our parent? All right. So we put a parent here and parent. All right. So we've got a parent. Isn't that pretty? So, and this, there is no line here. What I'm going to try to tell you here is there is no line here. No, the parent never ever has to communicate with the middle children. I'm sorry. It's just the middle children get left out. They are not important, man. The parent hasn't got no time for that. The parent's too busy with the first child. It's like, okay, you're my firstborn. I'm Odin. I am going to make you the king and you're going to do everything. I'm sorry. It's just the most efficient way. All right. So there's no relationship between the parent and the root. There's a relationship between the parent and the middle children. Middle child. I just can't stop saying that. Okay. So here we have the first one and the last one, right? And of course, the last child doesn't get any. This is actually working really nice. So the last child doesn't get any attention from the parent. Well, maybe they do, but they actually know who their parent is, right? So let's do that. Sometimes the parent discards a child because it is whiny. It's actually true. In technology world, it's true. So we're gonna click. Oh, this is a great Sunday activity. So anyway, here we go. So let's do this though. I like this one better because this now says, So the middle children, it's more likely that the middle children want to know who their parent is. Now they might communicate to their parents sometimes, but I don't know. Don't read too much into it. All right. So, so what I'm trying to say is that all of these, every single node has all of these relationships, right? So we have a first child, a last child. So if I want to get anything done, right? If the root wants to get something done, what does it do? So there actually is a communication between, that doesn't fit. I need to make it fit. There actually is a communication between we're going to do a shortcut. I'm going to wait though. So if I want to get something done, the root says to the first child, hey, I have a thing. And then it goes to the first child says, hey, do I have a sibling? I'm an only child. I don't have any siblings. Okay, we're done. The root says, okay, communicate, do this thing. It's like, the first child goes, okay, I have a sibling. Okay, I'm going to go do this. I'm going to give my sibling the message. And then the sibling's going to say, do I have a sibling? Okay, great. I'm going to go do it. And then this sibling's going to say, hey, am I the last child? Do I have a sibling? Oh, I don't have a sibling. Hey, look, I'm the last child. So I'm the last child. Okay, I'm the last person to do any work, right? And potentially the last child can then communicate back up to the root, but we really don't need to do that. As long as the stuff gets done, there's no communication going on. In this particular case, we're just having everybody dump out their pockets, right? And then we are observing the whole thing. So we have sort of an external observer over here. And so, we're doing that thing. There's not a lot of communication going on between the parents and the stuff like that. In fact, some of these relationships are redundant. Like the idea that you are a sibling implies that you have the same parent, right? So you almost don't even, these siblings, these nodes down here almost don't even need to know who their parent is at all. Because as long as there's a first child and it knows the parent, that's fine. The problem is any one of these children could die. And if those children die, they need to be able to step into their new role as quickly as possible. That means if there's a child over here and this one's not the last child and it dies, that means this one needs to take on the role of last child. And that means the same thing goes for first child. So, this needs to know which one the first child is. So even though it's a little bit redundant, it's kind of important that each one of the nodes, each of these nodes knows what their relationships are. And then we are going to update those relationships so that they can be traversed in different ways. Now, the amount of referencing you put in each node is kind of dependent on what you want to do, but it's usually easier if you keep, at least these minimal number of relationships to be able to just kill a middle child and have everything work. By the way, how would you do that? So if a middle child died, that means that in this case, the first child's sibling to the right would become the last child, and the last child, hi Zeddy, and the last child's sibling to the left would become first child, right? And they would go away. So if we want to orphan somebody out of here, all we do is if you want to extract one of these children from the family, I know this sounds really morbid, but if you did, you would take a node out, you would delete all of its associations, and you would patch up all the associations for all of the things that it was connected to previously, right? It's another reason that we don't want a parent-child relationship here, because that's really hairy when you delete a child to actually tell the parent, hey, you have to maintain a list. And anytime, here's the goal. I'm going to put a big thing here. So wait, where is it? Put a comment. How about that? No, that's not going to work. That's not going to work. Okay. So I'm just going to write it here. Italics. How about that? Beware of lists. Anytime you think you need a list, rethink it to use a single relationship reference. If you might think you want a list, but you don't want a list. Because if you have a list, then you can't do the stuff to the list that you want to do to make it, usable. And I do not know what's up with this, but there we go. Okay, so I'm just gonna put that there. Just leave it there for a reason. I'm not a graphic person, so I don't feel like that's what they use the same way. I need to justify this to the left. Text justify to the left. Okay, so yeah, so when you think you want a list, so you think you want to put a bunch of children in here, right? Well, the problem as soon as you do that is then you have to like maintain. You have to identify how many of those things are going. You'd have to update the internal list all the time. It's always easier to update a reference, which in memory is just one thing, right? Than to update a list. A list is a dedicated amount of memory that has all of these references in it, or the values and stuff like that. So you don't want to do that. So the advantage of using a structure like this is the fact that every single thing that belongs as a member all knows its relationship and can live independently, and so then you can add stuff to it. All right. Now I'm going to be writing a lot of code, and I realized the last time I did this, I didn't describe this stuff as well. So I want to make sure to do that. And such. Okay. So the truth is, these guys don't even need to know their parent. I mean, we could know their parent, but in our particular case, I don't need to know who my parent is. I don't, because I'm never going upstream. It's always stuff is always coming from the root and going down. So I'm going to delete that relationship because I don't need it. Now, it turns out I'm missing out on that and I need it later, I can add it back. But my particular case, so this is why graphs and graph theory is so advanced and fun, because there's a million different ways to proceed through this graph of relationships. Was use lists for working with trees. Was to use lists for working with trees. Yeah, well, we're working with trees, but we're not using a list. You're talking about linked lists. Yeah, we're not going to do that. So we're going to do this in a way that has no relationships other than these things, because we have one purpose. We want to traverse the tree as fast as possible. So all of our relationships are going to exist in our tree that are going to be optimized for walking the tree the way I'm going to be walking it. So as I said, though, there's many, many ways to do this, but they don't need to have a list in each thing, right? Anytime you put a list inside of it, we're talking, okay, so this is something else I have to be careful to talk about. So a list is different than an array. I know that sounds crazy, but if you're talking about memory, right, and you're like, these are all of my relationship stuff, we're not talking about that. We're just talking about the logical organization of, I have a thing and it has a child and I want to get through all of them as fast as possible. Now, I am going to do something here that might rub people the wrong way, and I don't care. I'm going to do it anyway, because what you could do is you could also you can still have children. So root can still know about its children, but how could you do that algorithmically? You could say, I want to know my children. And you could create a function that says, go to the first child and then go all the way to the last children. And then now I have a list of the children. And if you knew that you were going to do that a lot, you could actually cache that inside of the parent, and you could actually rewalk that so like if you actually deleted a child and you knew you did, you could go to the parent and have it recalculate its children if you're interested in cache like that. But I'm not. I'm just interested in a fast way to manage the things in this node tree. So, and I'm guaranteed to always have siblings to the left and right that are at the same level. And so this is this particular type of node tree that I'm working with. And I realized the other day that there are so many different node trees out there that this might confuse some people, particularly people who like Void, who's been, to university and seen all this stuff about graph theory. Okay. So my interest in the tree in this particular case is because I want to make an AST, and actually, by talking about it this way, I'm inclined to rename my package, instead of naming it rooted node tree, to actually name it an abstract syntax tree. But we're going to go ahead and just keep this and see where it goes. Okay. So this is what we're building. And I am going to jump right in now to how to do this in Go. So, I've already created a repo for this, and I'll just recap the steps, for this actually. You know what? Let's do this. Let's do. Yeah, I mean, I could do the steps again for how to build it if you guys want to know, because this is this is all from the previous video. So I think let's do this. Let's do this. Let's do. I'm gonna move tree dash go to tree dash go dash a rig. All right. So this is how you make. I'm gonna do this really quickly. Okay. So we're gonna make a new repo. First of all, let me get rid of my other one. Tree dash go. That's the GH tool. Okay, so this is how you make a new Go project, and I'm going to do it really quickly because I'm going to try to keep this stuff moving pretty fast today. So the first thing I'm going to do is I'm just going to make a directory inside. I made the directory inside of my RDBX raw repos GitHub directory, and within here I'm going to make a new directory. I already have a directory for my username on GitHub. I do this so that I can organize all of the many projects that I follow and work on and stuff, and just go look at them, look at the source code really quickly and know where they are and stay organized. And I put the github.com in there because one time I was using a bunch of stuff from GitLab. Occasionally I still pull stuff down from like, Google Code or some other Git repo, source hut. So that's my chosen organization for repos. I put a repos, it's in my environment and I can find it and blah, blah, blah. And I have a little tool that helps me out. I used to get around to all this stuff. So first step to making a Git repo with Git is to just make a directory. So we're going to make a directory called tree-go. I'm going to cd into tree-go. And now I have to do what? Well, we have to make it into a repo. So we get init, and that just makes it into a repo. And I'm going to go ahead and add a few files here that I've already added. So I won't take any time doing that. I'll just do my old one. Tree-go. Did I must have done it in the wrong place. Yeah, I did. Tree-go a rig. So we're going to put a README file here. There's not much in there. Rooted node tree and go. And then what? I'm going to go ahead, since it's an open source project, I'm going to put my other stuff in here. So I have a DCO file, which is just a developer certificate of origin file, and an Apache license that are in here. I believe you should probably start all of these the same way. If you want to, with GitHub, you can make a template, and then it will just give you a template, and you can go for it. So then we're going to open up the README. So that gives us something to commit, right? So if you look at status here, it's like, I don't know about these files yet. So we're going to add those files. I'm going to do full commands here so that you guys can know them. So git add -a dot, that adds all the files recursively. Check the status. You see, that's just to get, this is just, so I should probably not use the shortcuts, but I'm so used to them. So this is just git status. Git status. I probably could have typed it, but I'm lazy. So now we need to commit that, right? Well, we can't commit. We can't actually commit. So let's go ahead and commit. We don't, you can do everything with a GitHub repo without putting it in GitHub yet, if you want to. So the order of commit versus added as a repo is kind of up to you. So we're going to do git commit. So git commit. I'm going to remove, I have an automatic hook that's generated in my GitHub that I'm going to remove because that is going to allow me to commit to main. Committing to main is usually a bad idea. So I have a little warning on that. In fact, why not? Let's just make it into a dev branch. We don't need to be fancy here. So let's do that. So I'm going to branch this into dev. So now I'm in a dev branch, and now I can commit, and I'm going to say add initial files, and then I do, so that's committed to dev. Now I can actually change that branch over to main. So I'm going to do git branch main. And then I'm going to switch to main. This should know it, actually. Nope. So this is a git switch main. Okay, so now we're on main. Git branches. It shows you all of the branches. Wait, git branch should show you all the branches. There they are. So now I'm on main again, and I can go back to dev if I want to, but now I can actually go ahead and push main. So you do git push. And it's like, oh, you can't push. So I need to do git push -u origin main. Wait, what did I do wrong? I did something wrong. Someone help me out. It's probably because my other one is good to go. Oh, it's because we didn't do a. Okay, so this is where I'm going to go ahead and do the GH thing. Uh, so I'm going to do this in here. I'm going to do GH repo create, and it will detect the name. And I'm going to say rooted node tree in Go or something. And we're going to say enter, make it public. Do you want to use this? You want to add an origin, and that's why I always do this. That's why I can't remember how to add an origin. It's not that hard, but I don't remember it, so I always do this. So now I can do git push -u origin main, and that will push it up, and I can actually now open that in a web browser, and there we go. So there's my rooted node tree. There's some initial files in here, and we're ready to start making a Go project. So that's how you make any kind of GitHub project using the command line tools. But we're ready to start doing some development. So I'm going to be a good boy, and I'm going to go back and switch. It's just git switch back to the dev branch, and I'll be working on the dev branch for now. And let's take a 5-minute break, and we'll come back, and I'm going to keep the Pomodoro sessions down to 25 minutes. And so we can do that. So we can kind of move quickly on this. But so let's take 5, and I'll be right back. Add a stream marker. I wonder if I can add a marker in here. Where are you? Is there a marker? I think there is. Does YouTube let you do markers? Do 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 do. Manage webcam settings. Oh, there it is. Mark. All right, so we added an editor there. I'll be back at 11:47. Okay, I'm back. And so before we get going here, we have a question from Twitch. Ata Kui Exorcist 61 says, "Why has my branch been renamed from master to main?" That is a huge question that ultimately for me boils down to main is shorter. So I have set in my git config, I have the latest git, and I've set in my git config a setting that changes the default branch to equal main. So that every time I make a new branch, it's main, right? You can actually change that pretty easily on your own. Here's another command I have called default main, and this actually will rename the branch master to main. Main is the new default on GitHub, and I like it better. Honestly, it's just shorter. It's more succinct. It's more to the point. I don't particularly think that the word master had any racial connotations personally, but there were a number of people who did think that way, and so therefore it was changed at GitHub, and the Git project decided to make the option for people to make the change themselves if they chose to, rather than to take a side. So that's why. Honestly, though, my involvement with that is mostly practical. I just like it. And so, yeah, it's just, you saw, I only have so much space on my command line anyway to show my status. Why would I, throw in another, extra two characters? Honestly, I like it. It's easier to type too. It's a lot easier to type. So back to our rooted node tree work. We are in the middle of a project is not a human. In what way is that bad? We're not going to get into the politics of master versus main. I'm moving on. If you want to have that fight, go do it someplace else. I'm not interested in talking about that. Looking at your scripts and shortcuts, I'm amazed you didn't shorten it to M. That's fair. That's fair. No, I need it to be, relatively acceptable across the board. How's it going, Miguel? All right, so we're back to where we left off. So again, just to review, we're making a rooted node tree like this that knows very little about its family. The parent knows very little about its family because for my purposes, I only really want to traverse it from top down, and I want to get through it as fast as possible. And I'm okay with a little extra CPU utilization to figure out the children dynamically rather than to cache them and have to go through the business of updating it all the time. So that's the style of rooted node tree that I'm making right now. And we just completed creating our first development tree in Go. We have our Git. So we are all ready to start coding in Go. And I did this yesterday, so sorry again, I'm going to do it again. I'm going to try to get this entire project done today in one video, in one take. And I know it's going to take probably an hour or two, but maybe this will help you along the way. How's it going, Rakshish? So the next thing that we're going to do here is we're going to go ahead and we're going to make a Go project. Okay, so there's lots of ways to start a Go project. I'm just going to do it my way. So the first thing you do in any Go project, besides getting a GitHub repo started, and I think you should do that no matter what. Technically, you don't have to, but even if it's just private, right? The first thing we're going to do is we're going to do a git init. Well, we already did git init, right? That gave us our Git repo, but we need to do a go mod init. And go mod init, I'm sorry, I forgot that. You have to put the name of the repo. So I'm going to put the name of the repo here, and just do it. There's lots of other ways around this, but we're just going to do this because it's just the most practical. And that adds the name of the repo. So now we get a go.mod file, which is official, and the official way to do it since 1.17 on. You can get away without having a go mod files, but you sort of have to have them. Just don't try it. It's just a pain in the butt. So you just have to have it, even if it's just a command. Now this is a Go module, by the way. So a module, I talked about this yesterday too, and I'm going to talk about it really quick. A Go module is for all intents and purposes. Look, you can the purists out there are going to have fun with me, but I'm just going to state it simply. A Go module is a Git repo that has one or more packages in it and one or more commands in it. All right. And what's the difference between a command and a package? Okay. in Go, a package is a package that doesn't have a main function and a main package. A command has to be the main package, and it has a function of main. And if you can have a library, you can have a package in a directory, or you can have a command in a directory. You can't have both. It's one or the other in Go. And so it's really important you get that in Go. If you mix the two, you get in trouble, right? Now, this particular project that I have is just going to be a library, and a library is a module that just has packages in it, right? And even just one package in this case. So I'm going to be operating at the top. Now, it's very common on big projects like Terraform or something for people to create, there's no rules about this other than so they'll create, if it's a big monolith repo and they got all kinds of stuff in there, they'll usually create a directory called PKG for that sort of thing. But I don't want that. Why? Because when people use my module, I want them to do import this. Right? I don't want them to have a lot of extra stuff to do. And you only see the PKG directory show up in projects that are not designed to be used by others really frequently. They are like, all encompassing applications or frameworks or stuff like that. It is, however, not uncommon to see a CMD directory inside of a library. And that's usually, hey, here's some convenient binaries or executables that go with this library that you can use with the library. It's common to combine those. If you're from the Node world, they've been doing that in NPM for a while as the equivalent to the binary directory. Okay, so that's where we stand. So right now we have we're a Go repo right now. In fact, I can do a Go test and it'll say, sorry, no test, but you're good to go. So now what? Right? What comes next? Well, the next thing is we need to make the library. Now, I said this yesterday, but you can either make it lib.go if it's big, but another really common tradition is to name it the same, the main entry point, to name it the same as the library and the directory. The library itself will be named after that. So the fact that this directory is named tree-go has nothing to do with the name of the package, and that's a really important thing that I missed when I was a beginner. So we can name this foo if we wanted to, and then the import statement would be import github.com/rwxrob/tree-go, and then all throughout the code, it would ask you to use foo. In fact, let me just show you that really quickly. So we're going to make a test file right away. So let's do an examples test. Examples test.go. I like having an examples test more than anything else. So if I do foo test as is done, we can say this. We could say func example foo. I don't know, but watch what happens as soon as I save it. Output. I don't know. Do we have to have something, right? So, well, we don't actually. Okay, so now let's go ahead and just put a quick little function in here just to get it done. So let's say func sum say fmt println sum. I'm just trying to do this fast so you guys can get the sense of it. So we have a function here. And that automatically, my editor automatically added that. I should probably turn my ASCIIs back on. Okay, and then we have this. So when I save this, it will actually, if I do foo dot sum, it should do it. Go test. Undefined foo. Well, we needed to, we need to do our import here, don't we? So let's do our import. Import github.com rwxrob/tree. I'm trying to make a point that the package doesn't matter. Go, and I try to do this. Pass, right? So I passed. Why did I pass? Because my tree program outputted sum, but did you see how my package name, we're going to change it back, but did you see how my package name is foo.sum? Even though I imported tree-go. The point I'm trying to make is, you see what it did here? Actually, it added that on its own. It added this foo thing here on its own. And that does that to, that's my editor, that's my Vimgo doing that. Because if you don't do that, it's kind of unknown where the package name came from. So if it's good form to, if the package differs, to actually put it as an alias You can, by the way, do this to do side effects, and that just completely negates the use of the package if you just want the init stuff. I do that in command box all the time. So let's go back to using a good one though, right? So let's make the package name tree, and that's gonna change a bunch of stuff actually. If I change this back to tree, I'm gonna get an error. So oopsie, get rid of you. You're passing, but I don't know if you're in the right place anymore. Are you still in the right place? No. Tree rwx rob / tree dash go. Yeah, it is a convention. It's kind of a nice convention. So there we go. But now if I try to run testing in here, go.ts is my own script that just detects any changes to the files and says, hey, I can't do this. I've got 2 packages in here. What the heck? So the reason for that is because in my main file, I've got a package that's different. Now you'll get that error all the time if you're copying files from other projects and you forget to change the package name, which I always do. So some people would say that it's better to use an ID. It'll do it automatically for you on that. I disagree, but so we're gonna go ahead and do package tree, right? So now everything should be fine. Our test should not be as upset. So now undefined examples are like, I don't know what tree is. I lost track of my tree. Well, now I just did my save and then it auto imported the thing, is now I'm passing. Okay, so this is an example-based test. We introduce these, talk about them a lot. They're my favorites. They cause you to think like a user. It becomes part of your documentation. I think the first code anybody should write on any Go project should be an example test. In examples _ test. I strongly recommend that you adopt that practice because it's even better than, it's test-driven development in its best form because you're testing at the top level, the highest level interfaces into your thing. How is your thing going to be used in a way that can be explained in terms of what does this thing print out and what does it do, and that if you can explain it in that term, it's going to keep you on track, user base focus, and you're not going to get into the weeds. Now, if you need more lower testing for fuzzing and stuff like that, you can do it, but just start with your example tests first because now you're thinking in terms of user constantly. Okay, so and unfortunately, it's not talked about a lot. People do not talk about example-based tests. People don't even know they exist. And what are they? So this should actually be example sum if you want it to show up in the docs with it that way. There's a convention here for it's a word example followed by the primary symbols, which should be either a function or a type or an interface or something like that. And then if you want to test one method or function, then you would have an underscore, thing, and then you have the option of having lowercase stuff like that if you want to do it. You're going to see me doing it a lot, but if you get that right, then the documentation library uses reflection to associate the example and put it in the documentation right by that thing, so it's right there with you, and you get your docs for free. Yes, this is all going on YouTube. This is actually a live recording on YouTube. Are you not seeing it for some reason? It should be live on YouTube right now. Yep. Okay. This will be saved on YouTube, and it's going to be a part of a series if I don't finish this whole entire video. So if you need to come back and you're having a Sunday, that's fine. I'm just gonna go ahead and keep this way. But I think this is much better than a Hello World project for people who want to do Go. It does cover all the bases for a beginning project, but it's got some more oomph to it. All right. So here we go. All right. Yep. So this thing here, we're going to go ahead and we've got a start of our project. We've got all the scaffolding done, I guess is the word for it, all the beginning code. And I'm going to try really hard to not get sucked into the weeds right away and to stick with the basic stuff. Okay, so let's actually give some thought to what we want our thing to be. So what are our developers going to want to see? They're going to want to get a new tree, right? So how do we give them a new tree? Well, there's a number of ways to give them a new tree. We could say, let's do that. So let's just test tree for now. Well, okay. So first of all, what are the things of our system, right? We have nodes, these things here, right? And we have this overall tree. So on the surface, it seems like we're going to have, a tree struct and a node struct. And I'm going to jump right ahead. I'm going to skip a whole bunch of conclusions on this point, and I'm going to tell you right now, all we need are nodes. That's it. Because every single node is implied to be the beginning of another tree. Okay? Because any of these people down here can also be parents. Right? This is a parent. Any node can be swapped for any other node at any time. Therefore, all we really have in our system are nodes. And if you wanted some sort of meta container for your root node, that was fine if you had other things you wanted to keep track of, like if you wanted to have attributes about the entire tree, or you want to have caching or some sort of event that applies to the entire tree. But I'm going to be really bare bones because this is AST. And so in my system, the only thing in my system is nodes. In my tree, all there is nodes. And so there is no tree. And I started yesterday, I started going down the tree path. And what was the first thing added to the tree? The root node, right? And you can do that, but let's just start with nodes first. So the base item of our system is going to be a node, right? So I have a tree node. Well, what is a node going to be? Is a node going to be a struct? Is it going to be, what are people going to want to do with this thing? So let's say someone was just going to create a new node and then join it in. If this is just them, I just want to create a new node, and then I'm going to do something to the node. I'm going to put content in the node, and then I'm going to jam that node into its place in the tree wherever it goes, or make it as a root and give it children. So how do I get a node? Right? Do I want to say, there's a lot of ways I can make them get the node. I could say this. I could say n is, node. I could say node is a new tree node. All right. And that would give me a new pointer to a struct. Right. And this is this point of decision making that I'm at right now is a tough time because the TDD approach, I'm doing TDD, but you don't really have to call it out as TDD. It's just the way you should do stuff. You think about how the stuff's going to get used first, and then you write out however that's going to be evaluated. It doesn't even have to be in code. You can write it on paper. My user is going to do this and this and this and this. My developers are going to do this and this and this and this. It doesn't even have to be a test. I don't want people to get pulled into this idea of unit testing early, and this is why I like example tests, because you're thinking about it as a user. And so that is, example tests are not mentioned in Effective Go as far as I know. They're not. It's really sad. There's so many things wrong with all the beginning documentation for Go out there. I'm just going to say it. So I'm trying to fight against that by doing this. So let's go back. So this is one way to do this, right? And then I could have this. I could have something like, I'm just pretending here. I'm like thinking like a developer. How am I going to use this thing? I could do like node. I could say node first child, right? Node first child equals, and then what? I could do a new tree.node, right? And then that would be my first. You see what I'm saying? So I can sort of start trying to think about how this would be. Now I could do a more encapsulated approach. I could do node first child, and if I wanted to do a more encapsulated interfacey sort of approach, I could say new tree-node. Well, you can tell that new tree-node is going to get old really fast. What that does, by the way, that's a built-in. New is a built-in that gives you a pointer to a new version of this structure. Now, it's fair to say that I'm going to want to do something to my node, and yes, it's a level of indirection. Some people would argue that this is the most efficient because there's not as much indirection. This is where the art of coding comes in. It's like, do I spend too much time optimizing and no time abstracting, or do I spend too much time abstracting and end up unnecessarily abstracting and optimizing early? This is where the art of coding comes in. So I'm just for the sake of experience, I tend to think that having a constructor is a good idea. If I make a new node like this, what if I want to initialize the node and stuff? Well, okay, so let's back up a little bit. We know from just this initial example test that we have a structure in there somewhere, right? We know we have a structure in there. So let's dive into that. So what would that struct even look like? So the wrong place. I might have to redo this. So tree-go. All right, so we have a structure in there somewhere. Let's do that. So this is being test driven, right? So we don't have functions yet. Get rid of that function. And let's start with a struct. So we have a type called node. We'll use a capital on that. We're pretty sure we're going to use this, right? We'll call it a struct for now. Now there's somebody out there is thinking, well, why am I not making an interface? I personally believe you should start with structs. And then when it becomes clear that you probably don't want to make it a struct, you should, move away from it like that. So we're going to start with a struct, and almost immediately we're going to turn it into an interface. And this is where the trade-off comes, right? And I'm going to show you what I mean by that. So struct, well, what does our struct have in it? So we have our diagram. Where's our diagram? We have this one. So let's see. So structs have a child. So let's say child first. Okay, and it's also a node. All right. Yep. So it has a child, and we have first child, and we have a last child. Good. And I'm making these pointers to nodes. That's important. Why? That means it's not an actual copy of the node. It's a pointer to some other node that exists, or it's nil. That's what the pointer means. All right. So, and then I also have, so every node, what else does every node have? Every node has a sibling to the left and the right. So let's do sib left and sib right. Right. And again, you can do graphs in a different way, but this is the way our relationships are kind of working out because of how we want to walk through our tree. So we have this good stuff here. We have a first child, a last child, a sibling to the left and the right. I'm good. How's it going, Hemant? So we have, we have kind of a start on this, right? Here's our struct. We made this a capital so that it automatically exports, so that it can be used by other things. Otherwise, if it was lowercase, it would only be visible to the package. And in which case, the only way to give one of those to someone would be to force them to call a method. I have to call a function. And so we're gonna leave it as a bare struct for now. Okay, and we're gonna consider whether we want to have this stay a struct or we want to add more to it. Okay, and that, by the way, that is one of the hardest decisions in all of computing, if you ask me. We're not gonna talk about that right now. That's a very deep topic. It's a great question, but so somebody from YouTube is asking, what's their take on TWMs over FWMs and SWMs? I don't know. I'd have to go make sure that I understand which ones you're asking about. You're talking about different models takes on it. Yeah. So, waste management. I'm sure that's not the one. Are you talking about window manager? We are not talking about fucking window manager right now. Sorry, I swore. It's such an irrelevant conversation to all of the world. I use a terminal. The terminal is my window manager. My window manager is Tmux at the end. All right, so let's go back down. Why would you ask that question in the middle of a parsing video? I mean, seriously, you have to know that it's not on topic, right? Window manager, there's no need for a window manager at all. All right, so don't ask stupid questions anymore. If the topic is if you're not asking a question that's relevant to what I'm doing, don't ask it right now. Go to the AMA in Discord and put it in there, okay? And I will answer it. I spent 2 hours on Friday answering this. No, I'm not mad. I'm just trying to correct a problem. All right, so, okay, so here we go. This is, so we have an example node here. We're going to go back to, now you said we have a parent. Now, the real question is, do we really need to know about our parent in order for us to go through this? Do we need to know our parent? We really don't. We really don't. You know why? Because every time I ever traverse this tree, I'm always going to be starting from the top and going down. And there, I swear, in that book right there, the Introduction to Algorithms, there's at least 200 pages about all the different ways to traverse a graph. So when you make a graph or a tree or whatever you want to make, going into it with an idea of what you want to accomplish is probably the good. But I'm a very practical person, and so I want a tool, and my tool is I want to be able to represent the AST of a document, and that AST is never going to be traversed from any level of bottom up. It's always going to be top down. It's always going to be a top-down walking of the traversal. So I don't need a relationship to the parent. I don't. I don't need to. And it's if I were to add it, it's just going to add more overhead for me to take care of and clean up those links and stuff. Remember, when I'm traversing, I'm going to go to the first child and I'm going to ask him what all his children are like there. And by the way, for every first child, I'm also going to say, hey, do you have children? And then the concurrency comes in. I'm going to say, okay, if I have a child, I'm going to go do this stuff for all your children, and I'm going to go do all this stuff for your children. But the thing is here is I'm guaranteed that none of these nodes are ever going to be associated with the same child. That's super important. So my particular node tree does not have that sort of situation going on, right? So I can take all of this stuff and I can paste it right here, and now I've got another tree that doesn't need to know about its other people. So we can say, but they do need to know down, right? So this thing here, is going to have to know, like I can have a first child here, right? So when it gets, there is going to be this kind of downward propagation. So not only am I going to be traversing to the right to get to the next one, but this guy can also go down to his children at the same time concurrently. And so at that's an opportunity for concurrency and speeding up. Now, if I don't want to do that, I don't have to. I could actually, this is another way to do this. It's like top all the way down. I go top to the first child. I could go all the way down to all of my children and then all the way back up and then go to the next one and go all the way down. Or I can add some concurrency and I can go to this one, send it on its way going over here, and then send that one down a concurrency path, send that one down a concurrency path, and every one of these from the top level on can simultaneously propagate through the rooted node tree, and that's the most efficient way to do it. I do want to do that eventually, but I don't want to scare everybody away. So right now we're just going to stay very parallel, very synchronous, and very top level. So the point of this tree is to be thread safe in a way that acting as children of two different nodes will guarantee no shared children. It's for a big project, the library thing. No, as I mentioned earlier in the video, this is for generating an AST. The closest similarity I can show you really quickly is in Pagan. If you go to pagan.dev, so go take a look at pagan.dev and you'll see the opportunity for an AST. Now, this tree package of mine, this module, might end up having multiple trees in it. So it might be that I have to name this a specific way, you know what I mean? Because this is got very specific usage. But this is ultimately my goal. My goal is to get a top-down tree that is guaranteed to never have any children share children in any way, so we can get that concurrency. That are multiple paths, you create multiple routines, each go through each node. Am I right? Yes, more or less. So in this particular case, when I get, so let me show you, if I wanted to, I mean, we could do this, right? So we could say that you go to here, right? But this also has all of that as well, right? So, and I can't quite put it all on the same screen. We'll try to put it down here. But as you can see, so this guy goes here. Maybe shrink it down a little bit. And I mean, you see what I'm saying? So here's where concurrency opportunities come in. Now, we don't have to do it concurrently. I could go from this guy to this guy, go down here, make sure all these guys get the message, and after the last child go, oh, I'm done. Okay, then I come back here, and then this guy goes to the next one. Yeah, and then I go down here. And by the way, if you want to know why concurrency is so important, because pretty much everything in the world is a graph model of some kind, and most of them are rooted node tree models, particularly the whole internet. So when you talk about, I mean, not the internet itself, but document object model. And so if I wanted to get a message to everybody here, I would go from here to here and to here. And at the same time, I would fork a process or a go routine or whatever that goes down here. Right? And I do the same thing for here too. So when I come here, what does he do? So he forks a process and goes over here, and then another process goes down here. So that means that this stuff is processing at the same time as this stuff and at the same time as this stuff, all of it processing at the same time, depending on how much RAM and memory and CPU you have. That level of processing is going to be wicked fast. And this is, by the way, this is how Go compilers and the Go compiler and other compilers sort of work. They traverse these ASTs, make sure the syntax is correct, and they just go to town. It depends on what you're doing though, right? So if in my particular case, it depends if you just want to get a message to everything, or if you want things to appear in the order that they appeared originally, which is what we see here, right? So in which case I want to keep it linear. I don't want it to be concurrent in that particular case. So in that case, I want to write out the beginning of root. I'm going to go to first child. I'm going to write out the beginning of the first child, and then if this has any children, I want to write out the beginning of the first child and then all of its children, and so on. And then when I come back here, and then what I end up is a very linear, kind of hierarchical outline like I have here, and that's how I got that. So that's what we're doing there. It seems hard without concurrency. It is harder without concurrency, but sometimes you don't want concurrency. In this particular case, I don't want concurrency because I am generating linear output. I'm converting from Markdown, going to an AST, and then having that AST turn into a document. So I actually want the order of the children and their children preserved, because I'm not just sending messages to all the nodes. If I were just sending messages to all the nodes and I wanted it to do stuff, then that would be a totally different thing, right? So in this particular case, I want to maintain the order. And the more I talk about this, the more I realize I really do need to give a better name to my project. I'm glad I'm rubber ducking this out, because we need to, so it really depends on what you're using the node tree for, right? And so in my case, this is an abstract syntax tree. It's kind of my focus as I go in Key Macro. So that's, I'm going to, I'm going to own it. And I'm actually going to call this an AST. Now, to tell you the truth, the way that we traverse all of these items in the node tree, that's, we can have a tree and it can have all these properties, maybe even know who its parent is. But you know what though? I've kind of talked myself out of storing the parent because we're never going up, right? So this just the siblings. Where is the two first childs? So this first child is the first child of this guy over here, or that node. So anyway, let's go back for a bit. So right now, I don't really need to know the parent. Now, here's a real design question. If I add knowledge of the parent to all of the things, that means that this tree could be traversed in other ways, right? It could be traversed in other ways, and I would not be limiting myself. I would have to add extra code to keep track of the parents when things get deleted and stuff. But So the real question is, do we want to do that? Do I want to remember the parent so that later on, if I want to start here and propagate up into the tree, I don't right now, but if I did, how would I do it? Right now, if I wanted to propagate up from a sibling, the sibling would have to go all the way to its first child, and then the first child doesn't even know its parent, so it would have no hope, right? So I think you're right. I think we need to add a parent. Okay, now it's going to be a little bit of extra hassle to do this, but let's go ahead and add it. And it does appear to be redundant, so we're going to add a parent. And the parent means that, so now we have, so that any one of these children also knows its parent. So let's go ahead and add a representation of that, right? So, and let's where's my parent word? So, I mean, again, I don't want to add things unless I need them, so that's why I didn't add it initially. But if I don't do that, then my tree is so specific. Oh, thanks for the sub. If I don't do that, then if I don't add a parent, then my tree is really, really just like a one-trick pony, right? It's only designed for top-down propagation. But if I add a parent, then that kind of opens up the possibilities to other people later, and that means I don't have to rename the package or have to come up with a tree/AST or a tree/ whatever, right? If I make each of these things know about their parent and go through this slightly bit of extra work to manage that, I end up with a tree that's more useful to more people at the cost of some efficiency. And this is really the trade-off. This is the art of coding. It's like, where are you going to make your trade-offs, right? I already made the trade-offs of not caching the children identifiers, right? And if by the way, if you're going to add caching to remember all the children, you can do that, but then you pay for performance. I mean, you get extra performance out of that at the cost of memory. And so you're constantly making these trade-offs. And And when you go into a node tree with knowing what your purpose is fine, but I'm feeling the tug of abstraction. As a developer, it's really dangerous, right? I get pulled into abstracting away something that could be used for any possible purpose all the time. And that is super dangerous because it's more important that you code specifically for a need that you have immediately. And it's not optimizing to code for that need. And then as you have another need, say, okay, I need to also code for that need. And this is making the decision about how much you abstract a thing is a really tough decision in most architectural, you end up making the wrong decision, you end up backed into a corner forever. So I think adding a little parent up that upward link is going to be fine here. So I'm going to have parent, first child, last child, second sibling to the right. I don't have to have anything about children, but I will tell you this. You want to know where we're going to get the children, right? Well, let's just go ahead and do that already. Let's just in case you're worried where the children are going to come from. So if I have a node reference, I'm going to make a function called children. Okay. And what does children do? So, children, I'm going to write the doc right now. Children, starts, with the child, first. And I can almost change these, I can almost do this way. I almost want to say first, last, left, right, but we're going to leave the longer names on there. So children starts with the child first, and then what we want to say continues with a child with sibling right of child first, to return a slice of child node references. Children of child node references. Of child nodes. Node references, reference points or references, same thing. So this is going to return a slice of node pointers, right? And it's going to go from one to the other, right? So, and it's actually, we can write this really easily and quickly, but I want to wait just a bit. In order to get it to pass though, I'm just going to return nil for now. Now, and nil is a valid thing. So, returns, nil if no children. So this is a legitimate nil return error, right? If no children found. Okay, so, and you got to watch out for nil on that, but we definitely would. So here we're doing it with a struct. Okay, now the question is, so we have an interface call possibility. So do we want to make it so that anybody can implement a node? Or do we want to make it so that we're starting to get to the question about whether we should make it an interface or not. And there's massive divergent opinion on this. Some people would say, yes, this is obviously an interface opportunity. Some people would say, no, this is a node tree. We want optimal efficiency, or an array of size 2 nodes. Why not have a slice of node pointers in node instead of first child and second child? Because you have to update it every time. That's the caching approach. The caching approach would be to have children in here, and then you would not be moving around. We haven't hit the main problem. The main purpose of a node tree is to be able to orphan any one of those nodes at any time and not have it impact everybody. All right. So if you take a node out of a child, so what you're talking about doing, so FromSol is suggesting, and this is recommended in books all over the place, that we should have an array, a list in here of all of those nodes, right? And that we would use a linked list or something like that, which you could do. You could do a linked list in here and then reduce the overhead of having an array or something like that. But if you give any node, if you have every node have a list, array, a slice, whatever you call it, of children, they're all different, but people refer to them this way. The logical idea of children, then if you delete, so if this has a child in here and you delete this thing out, now what do you have to do? So you can't just delete this out, right? You could delete out this root's cache of all its children, and so in that case you'd have to take it out and then recreate the list. You have to take it out of the middle of it and then recreate it. And that's fine if you want to use a linked list approach. But if you have another way to do that is to just have everybody only know about its references to everything else and then update all of those references. Now, the question is which one is less efficient? Which one is more efficient? Which one is less efficient? The one way of doing this would be to have, and I'm kind of going down this idea that Formsol is talking about, which is in computer science books as well, is like we just give each node has a list of all of its children. That's it. So, and then each one has a list of all of its children. It knows all of the references to all of its children. But then what happens when you want to delete a child? When you delete a child, you just delete it out of the array and you slam the array back together, right? And then what do you get? You get a parent who doesn't know about its child. The child could still live, right? But then that child also has, that child node could also have its list of children, and it could manage it that way, and so on and so on. So that is definitely a way to do it. But another way to do it is to just keep track of the references to the things. And the reason that I'm okay doing it this way is because this kind of usually at least the ones I've read, and maybe I got this wrong, but the way that someone suggests that you implement a list of children inside of one of these nodes is a linked list. It is a linked list. So what this is kind of doing is it's blowing up the idea of the linked list so that it's included in the node tree itself, as opposed to being an internal part of just every node. So every node has a linked list in it, and then that linked list is the same thing, right? And that's an interesting take on that. We might have to look for that and give that a shot. If we did that, then what would it be? It would be you would have just children here, right? Now, if you're going to do it, this is how most people would implement it, and I don't think this is the right way, because this is definitely going to this is definitely not going to release the memory at all. And that's why I don't want to do it this way. So if you put a children thing in here, you would say, I want an array of node pointers, right? And then you wouldn't have to have any of these things. So let's just comment those out, right? You have to know who your parent is, possibly, and you'd have to know all of these. Okay. Now, if you do this, then what? So it's really easy to iterate anything, because why? Because now all I have to do is just iterate through the children. But how do I remove a child now? Right? First of all, here's another thing. Can the child remove itself? No, it cannot. This particular model for this, the children cannot remove itself. I guess it could. Never mind, I take it back, because the children could say, because now we have a parent reference and I didn't have it previously. So if you have a parent, so let's do that. So you have a parent and you have a child, right? Then if you have this node say, I want to delete, instead of having a children be a function, if I want to delete a child from here, right? You could find the child, you could say child.delete, and the child would refer to its parent, and then the parent would say, okay, you are child number whatever in my list here, and then it would remove it from the list, and then it would fix up the list, and actually, because it's a splice, it would still leave all the memory underneath, and it wouldn't fix the memory in the array. So I don't like that approach personally. It's not only is it less efficient, I just don't like that approach. It's in this particular case for an AST, it's super hard to delete and orphan things. Whereas if I'm going to do that in this other model, I can delete stuff pretty easily by saying, if I have a node, all I have to do on that node is say, okay, I want to node.orphan or node.emancipate. How about that? Node.emancipate. And then what it would do, it would delete its reference to its parent. Actually, first of all, it would go to the parent. I don't have to do anything with a parent, actually, because that's why I said we don't even really need a parent. It would go to the sibling on the left and say, hey, your sibling to the right is now my sibling to the left. And it would link up those things, and sibling to the left would say, yours now this sibling over here. And if it had any children, those children would be adopted by its parent. And that's why we have to have a parent reference. That's right. I forgot about that. We do have to have a parent reference for adoption of the children. And then the children are all automatically linked to the parent, to its parent. So they get elevated, right? we to recreate a slice on every delete so that doesn't leave empty spaces. Right, and we're not going to do that. Yeah, we're not going to do that. There's just no way. The way that I'm talking about doing it, the only thing that's getting changed are like references in the individual items, and there's no rewriting of anything. There's just removal of references from the object. So I like this particular approach better. So again, if you want to, you can actually have node.orphan, and what that does is it says, okay, I am now my own node. I don't have my own children or anything. Right? And you can decide whether you want to give up your children or not. You can have like totally get rid of any of its associations, and then you can recreate the node tree. So let's talk about this. So let's say this sibling here decides it wants to become an orphan, right? So or it wants to leave the family. So it leaves the family. It goes over here. This arrow goes over to here. This arrow goes over to here. This parent is no longer pointing to the thing, and now it's over here, and it takes its whole progenity with it, its progenitors with it. It takes all its children with it. Now, if it really wants to say, go off the grid, I am done, it can go over here, and then all the children can get adopted by the parent, and the first child will get adopted by the parent. And since only the first child needs to know about that, I just have to change the reference in the first child to the parent. And now this parent comes here, but because this first child is like there, the real question is does this first child now have the same stating, whatever priority as the other children? Because this first child, all of these children just got adopted by the parent. So in fact, what you would probably do is you'd make this first child take the place of this guy, take this one out, and now you change this one to here and this one to here, and now you've just injected all of these children into the higher level of the hierarchy. So they just got higher up in the hierarchy. So I really like the reference approach because it's got all this other stuff sort of built into it. Cost of resources. The resource usage will shoot up exponentially, isn't it? Yeah. I just bookmarked this. Got to go. Okay. So this is how I've done it in the past. This is why I tend to prefer it. There's lots of ways of doing it. If we had a formal computer science professor in here who could tell me what's wrong with my approach, I would love to hear it. But I do not plan on caching information. Now, there is a cost here, and the cost is CPU. I don't need to go through all of my children regularly, enough to have them cached. Does that make sense? Whenever I need to iterate through all of my children, I really can do it through an algorithm. I can say, I don't need to go loop through a list that's being maintained here at the cost of memory and arguably CPU every time it has to be updated. And this is why people write theorems about this stuff, because they're trying to prove how much resources something's going to take. So in my case, the children, like iterating through the children is not a big deal. All I really do is I go to the first child and say, as long as I have a child to the left, a sibling to the right, just keep looping and doing stuff on that. That's it. And so this is effectively the same thing as having an actual list without having the list. And that gives you crazy gobs of flexibility in terms of organizing your node trees and stuff. And for me, being able to pull a node out of the tree and put it over here and do this thing is far more valuable across the board, whether I'm doing an AST or I'm doing like a mind map or something like that. I don't want to have to update all that other stuff. So that's kind of where I'm going with this. All right. So it's probably time for us to take a little quick break. I didn't put my Pomodoro on for today, so I'm going to go ahead and do that. So when we get back, we need to make a decision here. The next decision, so think about this for the next 5 minutes. Should we use an interface or not? And this is a question that is a tough one. We're going to have a lot of functions here. They're going to be adding things, removing things, right? Do we want to make this entire thing so that anybody could implement a compatible node tree and be able to plug it in place of where mine is being used, right? And that would mean maybe implementing a tree in a different way. And I think that might be, I'm gonna talk about, I'm kind of giving some of it up, but we're gonna talk about why I think an interface is actually justified, despite the fact that it is a little level of indirection to do that. But it makes it a little bit safer for us. We still have to have the functions to tie up all the things anyway. We probably wouldn't want people doing that by hand, because inevitably they'll miss a link and then they'll have something that's like linked in the wrong place. The possibility of having function method overloading, really fun. Yeah, just to store data. So we're going to talk about that. But let me take 5, and then we'll come back and we'll talk about that. Okay. I'll be back 12:41. All right, we're back. So, let's probably put a mark in that. Big Jim says interface and periodic functions. So, yeah, we're going to talk about that. We're going to talk about interfaces right now. And one of the reasons I picked this project versus some of the another easier project is because it actually involves a lot of the pieces of a larger project. It's not hello world, right? It's like something you might actually want to think about. And so at this point, you're trying to make a decision. Well, do I use an interface? Well, what even is an interface, right? An interface is just a thing that says, this is how these are the methods you should have. And it's very similar to methods in other languages, but the way you would do it is like this. I'd say type node interface, and we already know it's going to have at least one function, right? So that function would be children. And it's going to return what? Well, this is where it gets interesting. I'm writing HTTP servers. I already wrote one. There's a Go one on that. HTTP services, yeah, if you want to use it with context. So what is children going to return? Children is going to return a reference to a bunch of nodes, right? And so, and why did I put node here? Well, because we have a conflict. Because if I go back to my testing, it's going to give me a conflict, right? So it's going to say, sorry, you can't do that. You can't call two things node. And so the idea of using an interface is really just, there's just one main advantage. You can pass a node interface as a type, and anything that fulfills that interface, anything that has those methods can be passed. How that is implemented is completely irrelevant. And so I'm going to make the case, having talked this out and rubber ducked it with all y'all, that this actually does need an interface. We already talked about the two potentially different methods that have different, caching the children versus that, right? All the different possible ways to traverse this tree or to keep track of this tree that, that somebody that would read a computer science book and say, well, I'm going to put a list in here. I'm going to keep track of that versus I'm not going to do that. I'm just going to traverse, right? Well, the truth is we don't really care. The end user who's writing, we're writing our examples for, they really don't care. They just want to know how to use the thing, right? And this is the case. Let's go back to our example real quick. So if we're in our example, we were like trying to struggle with like, well, what do we tell them to do? So this is using the structure type, right? Well, right away, we already see, again, let's return to what's easiest for the user, right? So for the user, it would probably be better to do this, to say tree.new, right? And we could just say new node, or we could probably say no, let's do new node. So that means they get a new node, right? And we do all this work for them. And if we need to initialize anything, we can do that. Now, we've taken a hit by having a level of indirection. Every time you add a method or a function, you have another level of indirection, and a lot of indirection, too much added up can be bad. But for the most part, if it's making it clear for the user, who cares? Indirection is really important. And if you don't believe me, go. Clarity is more important. If you don't remember, go read the Golang IO thing and read about file type. So we have files. Was it file info? Let me see if I can find it again. Golang. So file info is a good example of an interface that has multiple methods to it. Normally, small interfaces are the way to go because you can combine them, but sometimes you want to use a big one. So there's lots of good examples of this kind of stuff in the standard library. So if you go to the file info, a lot of these things return, there it is, file info, same file. So file info is an interface abstraction. The file info describes a file and is returned by lstat and lstat. So this works on any operating system. So this is a real solid use of this. Now, this is new. That's new. Yeah, it wasn't do that before. So let's go look at what the file type of file info is. What type of thing is it? So, it was added in 1.16. No way. So they added the file system type to 1.16, which is super awesome, which means you can abstract remote network file systems and all kinds of stuff. It includes embedding a file system inside of your application. So I didn't realize that they factored it out and did it like this. This is really cool. So they did 1.6. This is good to know. So anyway, because as you can see, this is all information that could have easily been in a struct. In fact, in C, it is a struct. It's a struct. It's like the name, the size, and all this stuff. But, and by the way, how many times do you think file info is called? A lot, right? In the standard library, it's used all over the place. So I'm showing you this just to help assuage your concerns about that many levels of indirection on function calls. There are some optimizations. If some of these function calls, if all they're doing is returning a struct, they will be optimized away by the compiler, and you don't need to think about that. You just need to make clean code, and it's stuff that's easy to use. And in this case, they needed to abstract this because this information is not available to every operating system in the same way. So this is why it had to be made into an interface, because Windows and Mac and ASR, or M1 and M4 or whatever, they're all going to have to give this information in a different way in order to keep consistency across the board. So they had to add an interface. So then we get this type. So file info describes a file and is returned by stat, the file type interface. And you see what it returns, right? Now, something I want you to see here is it's returning a bunch of primitives. Usually you'll see primitives in an interface, but sometimes you'll see other interfaces returned, right? And you're not often going to see, there's when you're returning something from an interface, there's kind of an unspoken rule here that it should either be a primitive or another interface, all right? And that's only for interfaces. So in this particular case, you don't, it's very rare. I've never, in fact, I can't think of any opportunity, probably some, but I can't think of any cases where returning a pointer to a struct is a thing, right? Because that could just as easily have been another interface. Now you can do this too much, but the general rule that I've observed is that interfaces, so the methods inside of an interface definition return either primitives or other interfaces. All right, but but there's going to be a lot of other functions that are going to be returning specific instances of a struct that fulfill an interface. So there's a saying in Go, pass interfaces return structs. But I would add that there's an exception to that, unless it's an interface. So if it's an interface that's going to return another interface, like we do here, see this file mod. So in this case, it's not. This is actually just another type. This is just wrapping up the type uint32. But that's cool because it returns the file mode type. That means if they even change what the type is, they can. They never will. But if they wanted to, they could, because they made a type that encapsulates this primitive for some reason, right? So that's what's up with there. And I just wanted to show you that. So that after having done that research, I am okay returning a slice of interfaces. That means a slice of anything that fulfills the node interface. It could even be a different one. It doesn't have to be the same one. And frankly, we don't care, because all we care about are what are the methods to get into this thing. And if you come from Java land, and about Java and, oh God, what is it? I'm blanking on the name right now. Solid and all that stuff, right? Then you already know that you should be doing interfaces for anything. Well, so let's do that. Now, so what happens to my pretty struct that I just made down here with all these public methods and everything, right? Well, this is kind of fun, and this is something that I personally love to do, and I haven't run into any problems with it yet. And if I like to make, if I'm going to, okay, so first of all, most of the time, you're not just defining an interface in your package. You're defining an interface, and then you also want something that does the work of the interface. So you usually want an implementation of the interface to travel with your package, right? Otherwise, it's useless. It's just a bunch of like how it should work, right? So what did I do? I just made this one private and lowercase the name. And some might say that's a bad idea. I'm just going to do it anyway. Some people think that it's important that you put this implementation in its own directory. There's lots of different takes on this, but I've had success with this so far. I haven't got bitten by it. Maybe I will someday. Take an interface and return a concrete type. Yep. And so that's another way of saying it. And so then we have this node here, but do all of these individual structs, do all of these things inside of here, do they need to be public, right? Well, that's a good question. So, I mean, we don't have to. We could, if we're gonna do this though, we should probably, I mean, honestly, we should probably do this. We should do parent, and what does the parent return? The parent returns a node, all right? And again, it's a node, right? It's a pointer, and so what does this then become? Parent, and we actually could keep it uppercase. You could even keep this still uppercase if you really want. Actually, no, we can't because we're going to need to make an accessor for it. So we make it parent here, and then we're going to say, so the parent is what? The parent is a pointer to a node. So you can see we're making an interface and then a concrete type at the same time. And we can keep going down that path. What did I screw up? I screwed up something here. Oh yeah, parent. And so there we go. Now the problem with this is obviously we're going to need to set the parent too, right? So then we get into mutator land, and I do not like that. I don't know. So this is where I'm kind of struggling because, I don't know. This is where I'm kind of struggling because if we do that, we're going to be doing this, right? We're going to be doing set parent to a node, right? I mean, get the parent and set parent, and you mutator and accessor. And by the way, they don't ever put get in front of that. It's like very standard to do this. I mean, if we're going to do that. So the real question is having a struct here going to be fine? Could I get away with this and say that my parent is a node? Well, I'm going to tell you right now that I want complete access to an internal version of this thing so that I can the most efficiently do any of the other stuff that I need to do. So that means I'm probably going to need to do get parent, set parent, and all of this other stuff. Now, this is where it gets really, really crazy, and I'm inclined to not use. What are you talking about, Flavio? No, that's a C thing. So in this case, we want this. So, I don't know. I don't know. I'm inclined to. It can get really crazy really fast. So part of the problem here is like we still have to. If we start thinking about the user from the very beginning, which we are, then we kind of get into this weird place. So let's go back to it just for a little bit and see if we really need this. So let's take parent out and just have children. So invalid receiver type node is the interface type. Right. So this actually would now be node. All right. This is a tough decision, honestly, because how much do you abstract away, right? How much do you really want other people to be able to make nodes? Do I need to make an interface at all, or can I have it just be a struct? Do I just want to make it an interface because it's the right thing to do, so that people can extend it and make better ones later? All of these are good questions to ask, but they're also going to add extra work up front. So I don't know. So let's go back to, when in doubt, go back to what the user is going to be doing. So we still have an error in our testing there. So tree 18, line 18, we have a problem. Okay, yeah. So this has to be lowercase node now. So as you can see now, this is going to implement node first child undefined. Oh, child first, right. I'm just doing that because I want the documentation to show up next to each other, right? So that's why that's there. Wait, do I already have that open? Do I have it? Yeah, okay. So I should probably, there's a second here. Examples. All right, so now we have new node. There is no new node, right? We'll get rid of this. We'll change this one to child first. I mean, let's get rid of all those for now because I just want to get past this. So we have tree gets a new node. Now this node fulfills the node interface, and so I don't know, we haven't got into some of this other stuff yet, but we will. And that should undefined tree. Okay, we don't have that. So let's actually add a function here. And func, so this does not have a receiver. So we can just say new node returns a new node, newly initialized node. Okay, let's see. How about this? Returns a struct that fulfills the node interface. And that's important because the interface is now the law of the land. So we're going to do func new node, and we're just going to return a node, right? And this is not going to complain because why? Because even though I'm returning a specific struct, and that's important because that means I can use it throughout the code everywhere else, but it also means that I can do this. I can say new load, right? But because new node has a children on it, I can use it as, so in userland, so node declared but not used, let's say line 11, okay. Let's see here. So, all right, so node equals that, and then let's go ahead and print it. Let's just print it. And so again, so this here fulfills the interface for a node, right? And why does that matter? Because I can actually use that, and when I pass it to a signature other places, to a function called, variadic or otherwise. So let me see here, testing. So as you can see, so there's all the parent and stuff. We're going to clean up that output, and I did that the other time. We're going to do it really fast today. We're going to make it print in a way. We're going to marshal this so that it is in a nice, pretty way, and that's going to get into the structure of my nodes and what I want to keep track of. And this gets more specific the more we go along. And I don't know. We're going to have to decide how that goes later. Yeah. So that's coming, but it's fun. That's actually the fun part. So we got our thing working here. And now the real question I have here is, do we allow right now, okay, watch, right now I can do this, node.childFirst equals tree.newNode. All right, see that? I don't need this actually. I can directly manipulate the fields of this struct for better or worse, right? And the testing is going to see now it gives me a reference. So that's a memory reference, right? Not too big, by the way. So again, it's not that heavy of an operation. So here's the really tough decision we have to make. Do we want people messing directly with all of the fields from a node? Do we want that? Do we want people to do this? I'm going to answer right away and say no. We don't want people doing that. Why? Because when they come to this node tree, right, and they decide, okay, I want to delete this guy out of here, what are the steps that are required to remove this sibling from this associations? We already talked about some of them, but so the algorithm would be set first child sibling right to deleted child's sibling left, then set deleted child's last child sibling left to the first child, and then remove the parent and do. So we've already covered how many steps, right? So there's got to be 2 or 3 or 4 steps, and we have to get those right. If we don't get those right, we're screwed, right? The association will be messed up. You can end up with things that have a first child that's pointing to the last child, and the last child has no idea who its left child is, etc. And the whole organization of our node tree falls flat on its face and just completely broken. And then you get infinite loops and all kinds of crazy, horrible things. So the fact of the matter is, we don't want users messing directly with this stuff. We only want them reading it, and we want them to use other methods like add node, delete node, and things like that, so that those nodes are changed in compliance with that. Letting the user access directly burdens the user, but to upload the invariants of the tree. Exactly. So I mean, you guys, when we talk about encapsulation, and I'm being very practical here, but when you learn about that in college or wherever you're going to school, the reason this is, sometimes it's fine to give people direct access to the struct. You know what I mean? To the underlying thing, to do all of that. But this is a really, really solid case where we don't want our developers touching any of the internals of our nodes. We don't want them to know, we don't even want them to really even know that there's children at all. I know that's kind of a little bit weird, isn't it? We really don't. In fact, we're going to make all of this stuff private. We're going to start to return and expose the functionality of our node tree. And we're going to find out that we don't even need to tell the outside developer user that we even have the knowledge of a first child inside of our implementation, which allows us to change the implementation however we want over time. If we decide we want to have a different way of doing it and we want to have that little array, fine. That's the nature of encapsulation. So have we paid for it with the indirection from all the method calls? Yes. But as we've seen with file info and stuff like that, the standard library is full of stuff that's highly performant, highly, concurrent and safe for race conditions and everything that uses this idea of an interface. So when I have the old school kind of idea, like if I'm adding methods on front of everything, it's because of all the Java I did. All the Java with all the accessors and getters and everything, I was like, oh my God, please make it stop. And thank God Go did. Go gave us, zero values and all kinds of stuff to get started. So, but in this case, we don't want to mess with that at all. We really want to get out of that way. We want to get out of the way. And so we obviously we want them to see something much prettier than this when they see it. So we're, again, living in user space. What is this going to look like? So let's go back to here and we have the node. So the first thing we're going to do is we're going to make everything private. So, and as soon as we do this, I can get really crazy, succinct, and unreadable. Why? Because I'm the only one who needs to know it. Me and the people maintaining the code, right? So I can just do left and right, and people will know what I'm talking about. I will know what I'm talking about. But that's not exposed to the end user at all, right? That's not exposed to them. So first, this is first child, last child, left, right. So, and you start to see this when the more you go private with things, you don't want to make a lot of things public. So, but looking up all the children, yeah, hell yeah, we want that, right? Do we want the node to actually know about its parents? Well, remember all those setters and getters I was doing? When we really, really think about this, like practically speaking, from how it's going to be used, we don't need to know that. You don't need accessors and getters and mutators for all the fields of this thing. We need a higher level function. We need a function that says add child, right? And we don't care about all the accessors and getters and everything like that. Those things are irrelevant and dangerous and overused. So let me just tell you something else. If you find yourself writing a bunch of accessors and getters, just remember, this is not Java. This is not even Python. This is not Ruby. We are not in that business. Okay. We are in the business of providing high level functional value as much as possible to the end user. And that means, if encapsulating stuff away and then saying, no, you actually don't need to see that. You need to see the methods to make something happen. Right. So let's do that. Let's give our users something useful. So the first thing we gave them was new node, right? And I'm gonna cheat here because I don't want to create any dependencies in my examples right now. So I'm going to use a fun thing with printf. I'm going to say I want the type. I just want to print the type. What type is this that we got here, right? And this is going to be, it's just going to print the type of node. Now this is actually kind of fun. So let's go back to the testing. This is printf in Go is just amazing. So you can see here that this exposes what the type is, right? Now. But nobody can use anything from it, right? So let's give you an example. So if I try to do this, what happens if I do a printf and I try to print, I try to print the, I don't know, even the type. Let's try to print the type of node dot, what was it? First child, right? What would it print? Well, it's not going to print anything cannot refer to an unexported field. Now, I can, if I wanted to, I could expose that. And I've seen this done before. People will return structures that are private structures. This is private, right? But that have methods, it says, the internal members methods that are exposed. And because they fulfill the interface, they're okay with doing that. So if I wanted to do that, I could go up here to first, I could put an F here. And now I've got, it'll give me something different. Where's my test? So it'll be node first undefined. Actually, it has no filter method first, but it does have first. All right, so we do this, right? So actually check it. So now it does it. It says, oh, that's a tree node, right? So I'm just going to show you that because there are cases where you might want to export some internal element of your structure for some reason directly, because it doesn't need necessarily to be, if you do that, by the way, they can change it. Right? If you do that, if they change the particular to reference, they can change that and they can screw around. So we don't want them to have any access to that. We want to shut that down. So this, if they try to do that, it's going to print an error. It's going to say, nope, sorry, I can't do it. Right? So we don't want to give them access to any of the internals. We just want them to have method access. And so that's fine. But the thing that's really cool about this is I can use this internal struct in all of my implementations, and I can go directly to the structure really efficiently, and I don't have to go through the interface. This is actually one of the greatest misconceptions I had about interfaces when I came to them and go, you do not have to use the interface in your internal implementations of the structure, particularly if you put it in the same package, right? I made a mistake when I started. I'm going to tell you some of the things I learned the hard way. So one of the things I learned the hard way was that I would try to put stuff. First of all, I was returning interfaces like this, and I was not returning structs. So that meant that anything, and then I was calling them within my internals, which meant that I could only use the things that were exposed through the interface. And that's a bad thing. So once again, take interfaces, return concretes, return structures and directs and stuff like that. When you use the recompiler code to test on every save, I'm using GOTT. It's a program that I made that just checks for spaces, checks for any changes to the file, and then just runs it using the internal Go test framework. That's what's happening. So you can actually, earlier in the video, I go over that if you want to go scroll back or something. So we have this internal thing here, and then we have our exposed interface, right? And now thankfully I realized I don't have to have parent, right? A parent and then set parent, which is the standard way. If you have to do a mutator, this is the way they do it. They never ever put a get. That's the idiomatic way to do it in Go. And I mean, it's not complete, of course, but I don't need it. Because why? Because now I'm going to add, I'm jumping ahead of myself. We already added new nodes, so let's add another test case. So let's yank this function and paste it here, and then let's do another thing. Is it convention to have capital interface names and a small case type name? No, that is not a convention, Rakshith. That is a Go syntax requirement. Okay, so lowercase means not exported, uppercase means exported. It's a very cute Go thing that you will just be like, what? And at the end, you'll be like so grateful because you don't have to put private or interface or exported. Yeah, so that's what's going on. So this is an internal node struct that lives in this package and has no visibility outside of this package. This is an interface that is exported. You can actually have private interfaces if you want to. I don't know why you would do that, but you can. And you can have it be lowercase. So anything it begins with an uppercase. So this new node has to begin with an N. If it didn't, it would only be available to everything else within the package and not to anybody who's importing it. So that's the equivalent of export in other languages, stuff like that. Okay. And one of the reasons that we're doing this convention of package_tree_test is because we're forcing ourselves to write examples the same exact way the users would be writing these examples. So as they write it, as you write it, you're being forced to use the package names as a user would write them, etc. And in this case, new node, if I made it a lowercase, would not even be available to the user after importing it this way. So should the type interface have the same name? No, that is my convention. So so first of all, there's no need for you to implement. You can have a package that has nothing but interfaces in it, right? But generally speaking, when you're going to make an interface, you already have a struct that you're dealing with. Somebody wants to do some work, and you want to implement one of those interfaces and just make it so they can make their own. And in which case, you usually want to make your implementation of it private. And some people put the implementation of it in a different file or in a separate package. All of those things are totally okay. I just have chosen personally, and I haven't been told this is a bad practice yet, but I personally like to keep the name the same, and I keep the name of the interface exported as a capital, and I keep the internal implementation of that interface as a lowercase. So that's just, I like that because it helps me. Some people might find it confusing. I really love that because I know that when I'm working with it, that if anytime I use a capital, I'm referring to the interface. Every time I use a lowercase, I'm referring to my concrete implementation of that interface in a structure inside of the code. So cognitively, it's a lot easier for me to process that and to read, frankly. So that's just my own take on it. I haven't seen that in the wild anywhere in particular, but that's what's up. All right, so we have this. So we have a new one. So what are we going to call this one? So this one we should probably call new node now because we're not going to do anything with the node type. We're just going to say this is how you get a new node, right? Now I could have just done tree.new, which would have been fine, but I don't know. Let's do that. I'm going to do that. I'm going to do that. No. I'm not going to do that. I'm not going to do that. Every time that I try to leave the thing that's getting created off, I always get punished for it later. So there's no rule for this, but generally speaking, when you're going to make a constructor, it's not a constructor, but you want to put new in front and then you want to have the type of thing. So tree.new node, this is important because this gives you a new node. It's not necessarily part of the tree. If you're to do tree.new, what is that? Well, in my case, it's a thing that is just the root node, right? It could even make an alias for it, but I don't want to do it. So, I mean, I could do it. I could do that. I don't know. What do you think? I mean, it would certainly read nicely. I'm going to try it. Example new. So we could say root tree.new just for fun. Should we use something that nobody uses ever? We could use an alias. You dare me? You dare me to use an alias? Now this is really just I could actually call it that too. I could do this. I could say type new is it alias? I forget how to do them. I gotta go look it up. Golang aliases. Golang aliases were actually they were brought about from some of they're really old. They were brought about to do some translation. Yeah. So as opposed to standard type definition. Yeah. So you could do type new equals new node. Yeah, and you could do this. You could say new is an alias for new node. I mean, if people want that, that's fine. I like it because it kind of I like things. I'm a linguist, sort of. I did Russian and French and stuff. I like it when things read really nicely. And so if I'm not above putting an alias in there if it makes it read well. Right. So a new node, I might want a new node, but I want to put the node in a tree. What if I want it to be root? So tree.new. So I got a new tree and new is just an alias. So let's see what the testing looks like. A new node is not a type. Damn, it's a function. Actually I can do just a function equals. Yeah. Yeah, I know how to do this. I'm gonna make this happen. People yell at me. I don't care. Func. I actually have to do delegation here. I'm pretty sure. I don't think. I thought you could do aliases. I guess I got rid of aliases. New node is not a type. That's right. It's a function. Damn. So I'm gonna have to just do. A new is. I mean, it's indirection. Do I really want indirection? Just for the sake of the language? No. Ryan Dahl, those things that you think are cute, don't do them. I love that. I love that video. That's too cute. It's too cute. Node. So node equals new node. All right. So there. Just while I'm thinking of it, I'm going to actually add something to the docs. So I'm going to create a doc.go, which is a convention. It's not required. Doc.go package tree. And the way you do this, you always start with the words package tree. The first sentence is the thing that gets included in GoDoc, so make it count. Package tree provides rooted node provides let's see, provides an interface and concrete implementation of a rooted node tree. So yeah, I'll put this down here, put that here. I don't like this. I'm not proud. So virtual file system forget. Is there one? That's pretty cool. The cool thing, yeah, that's super cool. Originally, the file system beneath the Git repo so that they get in all the tools, see what appears to be a regular working directory. What? Only downloads objects as they're. That is super cool. Package tree provides interface and concrete implementation of the rooted node tree. And so yeah, a rooted node tree with only for a simple rooted node tree. Implementation of a simple rooted node tree where everything is a node. Let's see, no meta data or encapsulation of the tree itself. I just want to put that in there. Anytime I have a little thought, I'm just going to dump it in the doc and then come back to the doc and clean it up later. That's really cool, Eric. Thank you for showing me. All right, so we're going to drop that. We're going to go back here, and we're going to do children start as child first. So again, I don't need this anymore. Children returns returns a slice of all immediate children, not grandchildren. Right, children. And so we're going to say I'm going to return nodes now instead of actually, you know what I can do? This is an interface, so I'm going to return that because these are all nodes. So again, return structs pass interfaces. New node if you want an alias. I know you can't do that. You can do it with var, but it's not a true. You can do that, yeah. But then somebody's gonna reset it or something like that. I mean, I wonder if I can do it as a constant. I don't think you can. That's what the alias is supposed to be. Yeah, the aliases is supposed to be the same. So you should be able to do. I don't know. Let's do this equals. I have a feeling that's going to squawk at me. So constant initializer is not a constant. Yeah, no shit. Okay. Constant. Let's do. I mean, I know var will work because that's just a reference, right? But they have a thing called alias. It's not a thing anymore, I guess. Let's stick with var. The problem with var is that it will get, I I mean, I don't know. So, I mean, you know what? I like that one though, because Henry, I like your idea because this one is actually not, there's no indirection going on. It's the same exact reference. New is just a shorter way of writing new node. Let's do it. I like it. I'm all for that. So that's good. All right, let's put that in our test. Yeah, thank you for your info thing. Go to pair, maybe type between packages. Oh, wow. Wow, that's super cool. Oh, aliases, right? Yeah. Yeah, and people don't use them. And they're only for types, by the way. Yeah, they're only for types, I just found out. I thought maybe you could do it for functions. You can't. So functions we can easily cover the way we have, and that's fine. Yeah, let's do the examples. So new node, we're going to do... We'll go ahead and do new. So yeah, new. I mean, I like this better because I like to be able to say it's the root. I mean, this is, you know, I want to make it really usable too. So whatever. People can hate me for it. I don't care. You know what? Let's do this. Let's say, and okay, so new is exactly equivalent to new node. So yeah. Yep. I don't know. I mean, we could put him in. No, I'll just do this. Exactly equivalent to new node. I put that here. Again, I like making really good documentation, so I'm going to go ahead and make it from the beginning. New node, new. And then this one down here, I'm going to say, actually, no, I'm going to say root. I like the reading of this. Okay, so you could say root node equals new node. And that should be fine. I know I spent too much time on stuff. I don't care. Example node. Okay, so what we got? We got new node. And we don't have any access to the type, so we don't care. What is our next purpose? So we want to start adding stuff, adding nodes to the thing. And I need to set my timer. So Pomo start. What time is it? Because this day is going to end and I'm going to be stuck. 45 minutes on this. Constantly equals new API, OPI. Yeah, that's what I'm doing right now. Var constant old API. Can you actually define it as a constant in advance? Yeah, you can't do constant old API. That won't work. I tried that. No, you can't use constant. I just did it. It won't let you. I tried it. Unless I'm missing something. I was like the first thing I tried. Yeah, but it doesn't work. It might be old. I mean, let's try it one more time. But so yeah, what you're suggesting is this, and I would love for this to work. Yeah, constant new equals new node. Oh, I see what's going on. Wait. The constant old API equals new package API. No, constant new equals new node. That should totally work. Maybe they needed to do this. Oh, I see what's going on. So they want constant vnew new equals, how about this? Constant new node equals new node. This might be, I can see this happening. Okay, so because that's a constant, then it can't be changed. No, it totally can be changed. Yeah, it can totally be changed. I don't want to do that. So I think the var is going to get us there. I'm trying to make it so that it couldn't be changed, and that's the hard part, right? So because this does not work. Yeah, that's cool. I'll have to read that article. That's new stuff I've never done. Constant initializer new node is not a constant. So yeah. .api new package .api. Interesting. I wonder if I did tree dot new node. Define tree. Well, because it's the package. Yeah. Yeah, I don't see that working. We're going to keep it a var for now. If anybody comes up with something on that, we'll do that. The only thing that I don't like about that is that they can change it. They could change new to be something else in the code and have it, instead of making new nodes, it could make a new node that's not what they think. And I don't like that. I don't like that. That's actually insecure too, because if somebody sneaks a little bit of code in there and changes the constructor, that could be bad. But it doesn't go the other way around, right? I don't know any way around that. So, I mean, the one way to make it for sure would be to have it call the other one, and that's the most secure way to do it, right? So, all right, let's just do this. This is the most secure. I mean, this is honestly the most secure. It's an indirection, but fine. I was hoping we'd get array around the indirection, but I'm less okay with the danger than I am the indirection. So new, yeah. Well, if we do it as a function, then it'll just get inlined anyway. So I think my concerns about the indirection are misplaced. So we're gonna do new node, returns node, and then we'll just say return new node, and that's totally fine. And that'll pass package IO. For a constant, one name is interchangeable with another when the definitions use the same type of value. Yeah, but it's a function ref, and that's why it won't work. This is guaranteed to work every time. So this is plenty good. Yeah, this is fine. Because and this will get inlined. This will absolutely be inlined by the compiler, so I'm not even worried. So I'm just going to keep it like that. It's actually the easiest to read, so we don't have to do any craziness with constant definitions and stuff. A function definition already is the reference to it anyway as a function is a constant. So let's do that. Has a runtime constant. Yeah, I'm not interested in reading that right now, but yeah. Well, this is fine. This does the same thing. All right. So next, what are we going to do on our examples? But this is one line of code and it's already done, and I'm done talking about it. This is going to get inlined by the compiler, and it's the hands down the best way to do this. I don't want to read any other dealings with constants. If we're dealing with types, that's a different thing for refactoring. So this is what we're using. Next, we're going to go, they use this. Yeah, of course they do. So this new node for right now can be inlined, not inline, but put on a single line. Let's do something significant now. It's back to the world of like useful stuff. So what else do we want to do? So now we got rid of being able to make a new node. We want to add a child. So what are the use cases for this, right? So let's go back to our thing. What are the use cases to this? And we're going to go ahead and do add child. We're going to do, insert child. And it's funny because there's actually a lot of parallel to this in the JavaScript API for the DOM. Yeah. And so there's a lot of commonality between anything that's using a node tree like this. So the first thing we're going to do is we're going to do add child. So we could do add child, or we could just do add, probably add child. Let's do that. So if we do add child's not going to return anything. You could make it return a child, and that's useful, right? So we're going to add a new child, and it's going to return one, right? And then of course we're going to have a bunch of other things that are not implemented yet. If we're going to, let's actually think about the interface really quick. This is actually a good design technique, I think, is to think about all the interface and then comment out the stuff and then incrementally add them. If you add them too early, you end up, just do our parse syntax. Yeah. If you add them too early, the problem is that you can't compile or test anything because all of a sudden you're not fulfilling the full interface in your node struct. So the way to do it is to kind of add them as you go, and then, but let's go ahead and design them all. So we need to add a child. Actually, we need one that's not going to be immediately available. You're not going to think of it originally, but we're going to need to say delete. And you need to be able to delete yourself, right? And you can actually put some little comments out here. Delete self. And that'll fix up all its associations and stuff. Return all children. And I'm going to just put some of these so they match up. And add child, this is pretty obvious. Add child and return reference to it. All right. What is the interface? Where are they the same? We talked about that, like allow 3 times. Because this is an interface and it's exported, and this is an internal implementation of the interface that we're using, and I'm naming them the same because I like to name my things the same because that's just the way I like to do it. There's no reason that says you have to have created a concrete implementation of your interface at the same time that you make an interface. The interface is the contract with the world. That's the thing that really matters the most. So here we have add child. So we're gonna add a child, return reference to it. We know we're gonna have to have lots of children. We have a method for that already, but it's not really implemented yet. So let's go ahead and just keep commenting stuff out that's not yet implemented. All right. So what else do we have? You know what? I'm going to use long comments for this because it's be easier. No, it's not. I don't know what's going to be easier. We'll just do this. Fine. Okay. It said use PowerShell syntax for naming it. I really didn't. So we have add child, we have children, we have delete. If we just did add, I mean, we could do that, but that's not really. Let's just do add child. We could do, actually, let's not do add child. Let's do append child. And I'm taking reference to stuff that already exists in the world out there. I'm going to write all these without the comments, and I'm going to comment them out because this is driving me nuts. So we have append child. We're going to have insert child before. Insert child before, and it's going to take a node. And so that's going to take a node, and that's going to not return anything. I'm going to get rid of these comments right now too. I'm just going to, this is interface design time is like, just get your interface done and then do it. And then you can like document it. Cause this is like writing the Doxbury code early on. Add a child node that only has one brother. Oh yeah. We had fun with all the family references. Yeah. Insert child before, insert child after. These are all common. And, what else do we have? We have, append child. We have insert child before is like, you could do that instead of the first one. You could do all kinds of things. You could do prepend child. Yeah, I know. Tell your brother or sister. You could like add child. So we just do add child. If we did add child, it just adds it. So this is the design. It's okay to be picky with the names right now because this is what we're doing. Tell your brother and sister, your mama. Add child. So if we add a child, it just has sibling. Yes, we're going to do that. Append child. Actually, the sibling stuff. Well, we really don't need to know that. Oh, I see. Add child, prepend child, insert child before, insert child after, children, delete. Oh, we have orphan. So orphan gives up all your kids. So what we're going to say, no, orphan gives up your parent. give up parent, and we have another one. So delete is different than orphan. Give up parent, keep children. Delete parent, give children, keep children. Delete means delete parent, children. No, delete all. Just remove. Right, delete all relations. And self. There's another one though. I forget the name of it. Add child, stepsister. Has siblings. I don't know if we're going to need has siblings. I mean, we could have, I mean, I don't know. It's like the whole left and right sibling stuff is more about, is more about the relationship. It's not about, I mean, it's about how we're going to traverse the tree. It's not so much about stuff that we would need. Like, right? Do we need to know that? I think we should probably have next sibling. Yeah, we should probably have that. We should have node. We should have next. Next. So next returns a node, right? And next or sibling next or whatever. Get next sibling. Yeah, we're not putting get on anything. So let's do get next node, right? It's definitely sibling. So we're going to sib next and sib previous. So if you don't have a previous sib previous, a sib prev, the only reason I have it like that is so that you can see them in the documentation next to each other. Honestly, that's the only reason. You could do siblings. You know, we could do that. Siblings could traverse all of the siblings that you have, and starting with the beginning. So all siblings beginning with farthest with so all siblings beginning with all on left then right. So that's good. I mean, that's good. Let's have that. Like C panel. Oh boy. Yeah. So children, siblings, sib previous. So all children in order. Okay, all siblings beginning left and right. So what siblings should do is it should take where it is and go all the way to its left and then start there and go over them all and skip itself and then do the rest of them. And that's the algorithm, right? So, okay, so to the sibling to the left, and now we're doing left, right, sibling to the right. Insert child after. We don't even need child. We could just do insert before and insert after. How about that? And this is up to school. But you can actually make editors out of all this. People do. Those in an array can help with locality for sure. Yes. Well, VMT, we talked about that earlier. Were you here for that? We talked about how we're not going to do, we weren't going to do any kind of caching inside of it. We're going to just now, okay. So you probably have a lot of opinions on this because you deal with the low level stuff a lot more. One of the solutions here is to put, lists inside of the nodes and then keep track of all the children, but then you have to slice the arrays back together, right? Or maintain a linked list inside of the node. Is this right? And then you'd have to either way. So this idea of like, bottom line, we don't care because it's going to be internally implemented in a way that it's just going to expose some of the stuff. I don't think you care about what the older children are ever in. No, you don't. And you don't even care about your parent, really. At least in the case of I'm using an AST sort of thing. But if we want to make a generic tree that other people could use, we might want to have references to parents and stuff like that. So that's really the question. Do we really need to know about your parents and your siblings? I don't think you do need to have the siblings. You should have a free list to go with the array, yeah, but that can be implicit where the free node's either the data or the next free node. Yes, right. So here we go. I actually don't know that we're going to need to give people access to the siblings and stuff. We don't want people to be traversing this tree on their own. And I feel like we're not doing this right. I think I want to be able to delete itself. I want it to be able to delete its parent. I want to be able to add new children. And I want to append a child, get reason to see how I think. There are good, but we haven't hit any yet. So I'm thinking about AST stuff that I don't have, and I don't want to overthink what could be needed someday. Delete all relations and self. What's the whole point of this? I'm not. Why would I tell you that now, having already talked about that a lot? Go watch the video. This is not that I've watched the beginning of today anyway. So we talked about ASTs and talked about how we're going to get there and everything. So we got a node, we have an interface, append a child. So that we know we have, right? Because we're going to have to add a new child to this thing. We know we're going to have to get rid of children. We know we're going to have to delete children. We're going to have to orphan them. That means that we don't want them to have the same parent, but we want to have to keep all the children. We actually technically, we don't really need to orphan them. So we do need to delete them though. In fact, these are it. This is really all I need. Okay, yeah. So this, I'm going to avoid scope creep. All I really want to be able to do is add and remove children from the node interface and be able to walk the tree. And that is really important, right? So the walking, whether or not we put the walking in this interface, we're kind of getting ahead of ourselves. I don't think I'm going to put it in here just yet, but because this is just a node, right? You should be able to take the node. But if we're not going to give access to the internal siblings and stuff, we should be able to walk the tree. Now, this is where it gets really interesting, and this is where we might want to use a generic or two, but we can actually. I'm just compiling them. I'm getting ahead of myself, but we probably are going to want a walk. And what the walk does, and I like that it's an interface. Now I'm going to keep this for sure, because I like that it's an interface because that means you can implement the method of walking the tree differently depending on how the interface is implemented. So the person using this over here in example land doesn't care how the tree is being walked. It's left up to the developer to implement walk. But what walk needs to do is it needs to apply a given function to every single node in the tree, right? And we probably want two different types of walk, right? We want a synchronous walk, which is guaranteed to go through, everything in the order that it appeared. And we want probably an async walk. And I actually in the older one that I did, I had walk async. So between append child and insert after, append child adds it to the end of the entire list of children. Insert after last node would be the same thing. It's just kind of an alias for that, if that makes sense. But see, again, we took away the reference to last and and all that stuff. Let me say previous, and I'm going to say next. Okay. A node should have a value. Yes, it will be. It should have a value. Absolutely. I know it should have a value, but in my case, I have very specific requirements for this, but we are generically going to say, yes, you have a value. And the value can be any type. We're going to use interfaces here. So this is where generics come in, and you might actually find this to be interesting. You can, let's get the value. So the value or the content right now is an interface, and I know we're going to keep that. Okay, so the reason for this is this makes it so we can make a node tree of anything. It can literally be of anything. Generics haven't been added, but you can actually add them. I tested them. In fact, if you want to see the test I have, Docker start AI generics. Here's some samples I was doing with generics. So if you go into sample, a system, a container I built that it's got Go. So this is how you do Go right now if you want to practice. So what did I do? Oh, whoops. Main Go to. So this is no syntax highlighting, but so this is how you do it right now. And this is if you wanted to do the node. If we wanted to make our internal node struct, there's a couple of ways of doing this. If you want to force all of the values of your node to be the same, and they're all going to be strings, it's like, what is it, homogeneous sort of way of doing it, then you can just do node T, and then it will force a node tree of just strings or just ints or just whatevers. You cannot alter it if you do this method. If you want to have the value be able to be anything, you either have to do something far more complicated with interfaces, which I just do not want to do, or you have to do something more complicated with generics I haven't learned yet, or you can just make it an interface. And that's how all map string interfaces work for like JSON parsing and stuff like that, because JSON parsing is almost inevitably a map string interface, because each of the types that can be represented by as a value in JSON is not known at the time that it's compiled. And you have to cast them as you're going through with type switching and stuff, which is fine. I really want to see how some people approach that idea with generics later, but I was toying with the idea of generics right here really quickly, just to see what's up with this. So you can actually, this is actually a really convoluted one where we have to cast it as an interface before we can even do the type check, because you can't check the type T of just type T directly, which is really weird to me. But this does allow you to have one function print a number, and it'll just do all of that. So that's generics. If I wanted to add generics here, I could actually do this. I could do T any, right? And then I would just make the value T. And now I have a node. It's obviously not returned to support yet, but now anytime I make a new node, any of its children all have to be the same type of node. They have to be the same type of node here. And actually over here, I would have to do this. I'd have to do T here if I was going to do it. So if I was going to do it, I'd have to do it like that. And that would ensure, if I was going to make a node tree that was specific to strings or something, or integers, and that would force the entire tree to all be the same type. But I don't want to do that. I want my value to be any possible thing on planet Earth, so that they can put anything they want to in there, and then they can do the type checking at runtime to unmarshal it or deal with it in whatever way they want. However, I am going to have in my ST, I'm going to have a requirement that if you have a value, you either have a value or you have children. You don't have both, and I'm looking ahead at my implementation of my ST, which I've already finished, but I wanted to just touch on that again. So here's my AST. All this code's already been done. I'm just revisiting it with grammars, generics on my mind, and just looking at some other ideas for it. This is an AST that's parsed from my Pagan grammar currently. It uses a lot of the same ideas I'm doing with the node tree, but I've always wanted to factor out the node tree from my Pagan project into its own library so I can just reuse it. And that means adding values back. So the Pagan one that I have does not have any reference whatsoever to a value. I take that back. You can have a value, but I actually stopped it. If you set the value, you can't have children. This is another reason it's kind of funny because, it's like, if you have children, you can't have value. It's like so bad to say that. If you don't have children, you can have value. You can be a leaf node. Because I don't want there to be things in my tree the way I was looking at it. I don't want there to be things in my AST that are both values and have children. I just don't like that personally, and it just makes it more complicated to parse. I also hate attributes. People have mentioned that before. Like they want to give nodes attributes. Right. This is a really common thing. Maybe we should just add them. I don't know. I think this is a horrible idea personally. So
a graph database or something like that. No, I'm just making a basic node trees that parse AST stuff. But I want to be able to use it for other things besides that too. So I'm kind of revisiting it. So map string interface. This is a common way to do attributes, you know, and then people make these convoluted node trees that you can't read. I mean, this is what you look at, you know, like do Docker or whatever, like do an inspect element on a web page, and you'll see this kind of crap, right? So you'll see all of that stuff. Node trees get crazy complicated as soon as you add a bunch of things. And so rather than doing that, I am opening up the value to be whatever you want. If you want to bundle inside of your node a value that has got all of these like amazing different things and stuff in it, great. And by the way, that value will never be another node. Now, strictly speaking, there's nothing stopping you from making the value of a node another node tree, right? And some people would argue, and I actually played with this morning a little bit. Some people would argue that you don't even need all this parent stuff. You can just have another node be the only value, right? And then does it have children, et cetera, et cetera. And I don't want to do that. There's also another thing that I'm going to add that I'm going to like inject into this. I want all of my nodes to have a type, and the type, or I guess we could call it kind. What kind of node is it? So the node kind is an integer, and it's always an integer. And this is how you get this really great short form. I stumbled on this last year while I was doing this, and it's one of the best, accidental mistakes I made. This is long form, but these names here are just representations of numbers. And the reason for that is because in short form is like really short. So I don't think I have short form listed here because it's almost impossible to read. Here it is. Short form, if I can find it. That's the AST. No, that's long form. So short form basically is the same, but without these things and without the white space. And it's hands down, it's the fastest parsable JSON that humans could create because it's just an array and it doesn't waste a single character on anything. It uses ints for the type, which doesn't require quotes. So the total amount of size necessary to store and transport over the interwire, I did this because I hate the AST for Pandog. It's like way too verbose. So that's why I did it that way. But we're not going to put a value in here. Actually, no, we are going to put a value in here. We're going to have a kind. So kind is just an int. And yes, you could infer the kind from the value, right? But I don't want to have to force people to go through inspection of the interface value to identify what the type is. There could be a type mismatch between this, and that's fine. But if there's any metadata at all in my system, that's it, right? What is the kind? And so when you have a node, that sounds like we're going to have a type, and we're going to need to set the type. So, yep, we're going to need type and set type. What's the type? What type of node is it? Well, let's use let's use kind, set kind. Should we do type or kind? What kind of node is this? Should we do kind or type? Type. What type of node is this? What type is it? It's I kind of like kind better. I don't know. But this part has to be set, and the value, right? So the value is the only other accessor that we need. Actually, you know what we should do when we do a new node? We should force new node to take what kind and a value. Yep, that's definitely what we should do. So now you have a new node. You have to have a kind and a value. I like that. Kind and a value. So, yep, and then I can change these actually. Renode kind v. Kind v, because type's going to get me in trouble. So, kind v return no node. Actually, that's not a thing anymore. So now we need to do this. I knew we were going to need initialization pretty much all the time. Return node. No, we'll use n. So that's, yeah, n equals new node. I could have done it in one shot. It's a little bit harder to read that way. So I'm a fan of this. I don't know if it takes longer to do that. It probably does. Let's do this. Let's do this way. Let's say a node, and we'll take a reference to it, and we'll set its types, and we'll say that its kind is a kind, and its value is v. That's probably the fastest way to do this. In fact, I could just return that, and that's going to hands down be the fastest way. So, I mean, a lot of that stuff would be inlined, but I think that's fine. It's been experience learning algorithms, data structures with it too. A bunch of while ago. Oh, nice. Selective duplicate. It's good to hear. What's the difference between append child and insert after? Okay, you asked that already. New node kind. All right. So that takes a reference to a new node. This makes a new node and it assigns these values. I use a key value pair combination so I don't get yelled at by the linter. Even though they're the first two things, I could have just put them in order, and we should never depend on the order according to the linter, because changing order in your structure, all your code breaks. So that's it. So we have a kind and a value, and we get a new node. And then what? We got 11 minutes left until I go on break. And I'll probably go. I might actually, what I might do is, well, I'll talk about it in a bit after we get this done. But if you want to, you can run ahead and start implementing all of this. But these are the interfaces. This is what I want my user to be able to do. They need to be able to set the kind. Actually, no, we should never ever allow them to change the kind. Ever. It's super important, because we want nodes to be not ephemeral, but we want them to be sort of, they just do not change, right? Do we want to be able to change the value of the node? I'm going to say no. So when you make a new node, you better damn well know what you want to do with the node. You should not be making a new node and then screwing around with its value. And that's a stylistic decision. That's not a best practice or anything. That's just like I want to make my developers think about what they're doing before they make a node. And so if they want to have a value that's been pre-initialized and all that stuff, great. Set a pointer as the value. Immutable nodes. Is that what they're called? Immutable, yeah. I want my nodes to be sort of immutable. Now, if somebody wants a non-immutable node, then they can actually pass a pointer value as a value, and they can go to town on that thing. But they better damn well do it in a way that's going to prevent race conditions, right? And if I were to add get and set on kind, that's not a race condition because it's struct, but still, you know what I mean? So it's up to whatever you want to put in your value for your node tree. But I'm going to say, look, you can get to that value, and it's like, set. I could put a thing here that says only set through new node, right? And so, yeah, I'm going to put read only. Because we don't want people messing with the values anyway. They should decide that you have a node and what kind it is, and then chuck that node. If they wanted, they could throw the whole node away. Right? I mean, I could actually force that if I wanted to. I could make the value not be a pointer. I mean, because it's an interface, it could be anything. When I originally did this, I made it a string based on Rob Pike's suggestions. Actually, Pike says you should usually use strings for everything, because you can or byte slices, because you can turn those into anything else. You just cast them to whatever, right? And frankly, an interface is essentially that same thing, but that's more recognizable to people that are in Go people. And so I'm going to actually put a note here. So this is where you really spend your time documenting. And unfortunately, GoDoc is really insignificant, is really lacking, I want to say, for documenting interfaces, because it forces you to do extra things. By the time you get a really good interface documented with the contract and everything, you usually don't need to document the rest of the stuff. You know what I mean? It's like, go look at the interface. And sometimes it's actually another reason to not expose public, methods and members of your internal struct implements interface, because then you have to document those too, right? So even if you return a private thing, if you have a public thing in here, you need to still put an explanation of what that is, because the Go docs will say, hey, you have a node here. This thing returns a node, your new node or whatever. And so that'll trigger the documentation of all its public things. And that means that you have to actually document them down there as well. So, and then you have documentation kind of all over, right? You have documentation down here for these things, which is fine, I guess, but it's better to just really document the interface well. And the way that there's lots of ways of documenting interfaces. I've seen it done so many different ways. I personally like to have the footprint of the interface immediately grokkable and readable, like I have it here. And then what I do is I put an extra heavy duty document for the interface above it, so that I'll say something like, kind, and then I'll go here and I'll put in its own line so it gets its own title and everything. And then I'll say, you know what I mean? And then down here, then I'll give a full explanation of what that is, what its contracts are. And again, this is of all the things you document in your package, documenting the interface is the most important thing, because the interface is what everybody else extending your package needs to know in order to make it better. They need to be able to say, oh, well, if I have a kind must do this. It must return the kind. It must be an integer. It must, you know what I'm saying? But beyond that, it needs to, if it's doing any internal things, you need to suggest ways that it should be doing that. And sometimes you want to say, well, it doesn't have to do it that way. Like children, for example, which I think we got rid of. Prepend. No, we need children. Sorry. We do need children. So, or children. So we might say this return all the children, but walk and walk async, those are different kinds of things. And so, like, for example, walk does need to have a suggestion in the contract and say this. You could, if you wanted to make your agreement with developers to say you can walk however you want on this tree. I mean, that's why I put a walk async, right? So the walk is like in my contract, I'm actually going to write it. It would be, so walk, so we could say, and it's unfortunate because you can't. So the other way that people do this is they document it right here. And I hate that, because they document it right here. And then it's like it takes you 10 pages to read the interface. And then they'll usually say, well, that's because you put all this stuff in your interface. You should just put, another way to do this too is to have interfaces that are interfaces of interfaces. Do you know what I mean? And you could do that, right? So another way to do this interface, and I've seen people do this too, and some people argue that this is the best way. They would say something like this. They would say, has kind interface, right? And then you would say, I don't know, man. I'm kind of split on this. So with a picture of a huge interface, I mean, huge, really? Well, the whole point of interfaces is if you make a huge interface, then nobody can. There's a lot of times people are going to need to use your interface, and they're not going to need to know everything about your interface. There's people who need to use your interface, so you want to implement some part of the interface without implementing all of it. And so this is the kind of the idiomatic way to do that. And I'm actually thinking about doing this. And by the way, if you do this, you just have to do this. I don't know if I want to look at that. So you can just do this. If you want your interface to be the composition of a bunch of other interfaces, if you're going to make a true node, like this has a node, you can do it this way. One of the advantages of breaking your interfaces down like this is then you can then document each interface by itself, and then you can combine them all, and then people can go look and see that they're all combined. So you could say has kind, it's like marshaller and stringer and all that stuff. You could say type interface with like 1,000 methods. Oh my God, no, that's stupid. Called app. That's completely stupid. Oh my God. I mean, it never worked there. So, oh my God. That's like so stupid. So it's better to break it down, right? So has value interface. The tweet could have been about that. And then you say, so then you can do this. You can say has value and then value. Yeah, but it doesn't let you set the value, right? So, and you could say, I mean, I'm going to do this. I'm going to do this because the reason I like this is because when you do it this way, the things that you write might implement, but not only that, not only can you test each interface individually without having to implement the whole interface for the whole thing every fucking time. Imagine that person with 1,000 methods in their interface trying to test that thing. Because if they change anything anywhere, it's going to automatically not fulfill the interface and it's going to be unusable. So the reason that you see the best practice of this in the standard library all over the place of having 1 or 2 or 3 or 4 methods per interface is because you can compose your interfaces together and then you can individually test those other interfaces or have people implement parts of your interface to use stuff from other things that they want without making necessarily as bad as that, right? So, if it's a value, so it has a value, it returns an interface, and so the other thing too is that this, the documentation I talked about. So append child. So this append child insert after and children, that actually all makes sense to put in a has children interface. All right. So, I'm going to do that. I'm going to put all these guys in a has children. So that means I can test has children all by itself, right? Now, this does have a dependency on a node. So there's sort of an indirect dependency on the node. This one might not be a good idea because you already have, it sometimes gets me, I mean, I still haven't been able to, well, the problem with this here, and I'm starting to think that having has children is a bad idea. Why? Because I already have dependencies on references to other nodes. Right. So since I have that, I have a tendency to think that I should go ahead and just put it in the node interface because it's got a bunch of references to itself. So that has to be there. Right. Same with delete. Delete. You could just make a deletable, yeah. So type deletable. I don't know. You get as crazy as you want or not. Too lazy to jump around and search for stuff. Deletable. But you see this in the standard library. So we definitely need walkable. Walkable interface. I think this is shaping up because there's no references to the other stuff. And so it has value. There's all the children thing. It has kind. We can actually has kind has append child. I mean, and then we could say what? We could say deletable and walkable. Deleteable. Is that a word? I don't know. Deleteable, probably not. You could say has delete. I guess not. Deletable. Yeah, I guess it is. All right, so deletable, deleteable. We could probably say removable, but deletable is fine. Deletable and walkable. So you can implement, these individual things without having only added that, and that makes your interface a little bit. I'm glad I did that. So that makes me really feel good about this. So, because not only that, but now I can test all the individual things. I can just comment on all the other stuff, and I can document them individually. And so a node has a kind and a value, deletable and walkable, and it has children. If I do has children, then I could put that into its own thing, but it's a fundamental part of being a node is its children, right? You're not really a node unless you have children and a parent and all of that stuff. Insert after. I still think we should probably put parent in here. I just cause. So we have a parent, we have children, we have siblings. That's what these are, right? Insert after append child, prepend. No, let's see. We could just do this. We can prepend a node and add a node, so that would be to the children. It's kind of implied. We could do insert before node and insert after node. We don't even really need that, right? I guess we do. So append. Oh wait, append needs to be node. That we need append here. We need prepend node. It's going to put it at the beginning of your children. So if you have a sort of in a list, but not really, put it in your list array. And then insert before. Insert before node, insert after node. And then we need, so this is for siblings. We actually need how to have a child. I don't know. Let's see. How do you decide which ones to embed inside the other interface? That's completely artistic. I don't know. The ones that are really locked down to the interface, so they have a node reference, I'm putting them in there. You can put them all in a single interface. Maybe this is unnecessary, but I like it. I mean, the thing that's cool about this is I can actually test the interface in other ways, right? It's possible that somebody might want to pass something that's walkable that's not a node, and so they could still implement a walkable thing, even though it doesn't have any idea of a node in it. So truth is, I might end up using these interfaces for other things. And this is where the stuff gets really interesting, right? Returns a node ref, yeah. So those are inside node interface, right? So these other interfaces, to tell you the truth, I might want to break out into another package. I might want to break out, kind and value and stuff into a different package at some point. So, yeah, I mean, I don't want to have to reuse a deletable interface. I want to be able to say, but I don't know where it would go, right? Would it be util? I mean, it's like all the marshalling stuff. It's all in FMT, right? JSON marshalling is in the JSON thing. So is it deletable? So this would be tree.deletable. Does it implement the tree.deletable interface, right? So I don't know. I'm going to keep that for right now. It might be overkill, but it's hard to say. I need to take a break. I'm probably going to drop the stream. I will start the stream back up later. And I'm just going to splice these videos together in a playlist or something like that. So far, I think this has been a faster, dealing with the whole thing. Not everybody's going to want to watch all 3 hours of the video, and that's fine. But those of you who do can go through these considerations while you go through it. I still have one decision that's kind of waning on me, and that is whether so if we have this just says, okay, I want another child after this one. So nodes kind of act like lists, by the way, right? So we have this prepend and this append idea. Append child and insert after. Yeah, see ya. So I don't know what we're gonna do with that. To tell you the truth, that is, we still have the add child thing, right? I think we just need to have add child. Yeah, we need parent. So insert before and after. All of these are related to the siblings, right? You could actually say sibling, stuff like that. Insert before node. Actually, insert before node, it doesn't matter, what that node is. It's going to put it right there in front of it. Prepend node. So that's gonna, yeah. And so then we have a parent and children. So see, children. So then we have parent. We have to have add child, right? And so, I mean, this is probably why they decided to do so much with this. You have add child, right? So you could have add child before. So this is insert before this node anywhere. It could be anywhere. I don't know. What, I don't know. Let's see. I mean, we already dealt with relationships before. I'm just kind of revisiting it again. How's it going? Welcome. Before actual content starts, everyone gets the notification. I do it every time. I did it this time. I relaunch the stream every time. Yep. Sometimes it doesn't take very long. I rechange the title and then I redo the notification. And notifications are weird though in Twitch. So I know the YouTube ones are working because when that happens, I get like 15 people in right away because they get notified. So we want to have add child. I think we're going to have add child before node, and then add child after node, and that's going to be. I don't even know if we need that, because all you need to do is find the child, right? You just need to find the child and then put it in there. Yeah, let's do that. Let's do add child is just after the last one. Add child before is in front of this node. Do we want to do new child is really the question. Actually, we don't want to return stuff here. Add child node. Okay. Add child after is after the last one. Add child before node. No, we don't want that. You know why we don't want that? We just want add child. Here's why. Because append and prepend. So if I add a child, if I have a parent, I can find the child and I can do child dot prepend and it will add child dot it will add one to the front of it. Siblings, we could say append node and say add after. I know I'm getting really sticklery here. Add before. So this would be like node dot add before node, and we could say add previous. How about that? Add previous and add next. Node dot add previous node. So they would add that node. It would inject it to the previous. Node dot add next node, right? And so yeah, we should probably have. I don't know if we're gonna have previous and next is probably okay, because people are gonna want to do logical checks. You know what I mean? They're going to say, is the next node something like this? Then I need to do something with it, right? Not only that, but if we're going to allow them to do walkable stuff, they're going to need to say, well, what is my next one, right? I'm going to look ahead and say, well, what is my next, and such. So add child, add a child to a parent just adds one right away. If I ever want to add a child in a different order, I could make a new node and then do add previous to one of the other siblings and do that. So I don't want to expose too much here. Because I feel like that could become a problem. It could Could become a problem. We could probably put some caching on there though. Actually, it's growing big. This is because no, it's not. No, it's not. Because see, they're all small. All the interfaces are smaller. Yeah. Deletable, lockable. Yeah. Yep. Add previous, add next, deletable, lockable. Yeah, I don't even know if you need interfaces for this. We could, but we talked about that, right? That's a good time for me to go take a break. I'm getting kind of hot too, so yeah, I think this is a good place to leave it. I'm gonna go ahead and save this. How's our testing, by the way? Yeah, we need to implement the interfaces differently. They treat that new node, not enough arguments. Yep, we got lots of stuff to do. I'm not gonna save this just yet, but we're gonna come back to it from an example point of view. I don't know when that'll be. It'll probably be later today. So watch for the notifications. I'm gonna go ahead and just cancel my stream for now and come back. I'm gonna go ahead and raid somebody on Twitch and stop the YouTube stream. So we'll see you in a bit.